Imagine staring into the night sky and realizing that everything you see, every tiny dot of light, every swirling galaxy, is just a fraction of what's actually out there. Now, take that thought and stretch it to an unimaginable scale. What if I told you that hidden in the cosmos are structures so vast that they shouldn't even exist according to the laws of physics? We're not talking about galaxies or clusters of galaxies. We're talking about something bigger. Something that bends the very rules of the universe itself. These are called Large Quasar Groups, or LQGs. And if you've never heard of them before, that's because they're one of the biggest mysteries in modern cosmology. They defy our understanding of how the universe is structured, challenge the limits of physics, and raise deep questions about the very fabric of reality. How did they form? Do they break the cosmic speed limit? And most importantly, do they mean our theories about the universe are wrong? To understand why large quasar groups are so mysterious, let's start with the basics. A quasar is one of the most energetic objects in the universe. It's a supermassive black hole at the center of a galaxy that's actively feeding on matter. As gas and dust spiral into the black hole, they heat up and emit an enormous amount of energy, making quasars shine incredibly bright. Some of them are so luminous that they outshine entire galaxies. Now, imagine not just one of these, but dozens, sometimes hundreds, of them, clustered together in a massive structure spanning billions of light years. That's a large quasar group. But here's the thing, according to our current understanding of the universe, these structures shouldn't exist. The fundamental principle of cosmology is something called the cosmological principle, which basically says that if you look at the universe on a large enough scale, it should look the same everywhere. No matter which direction you look, the distribution of galaxies and other cosmic structures should be roughly uniform. But large quasar groups seem to break this rule. Take the huge LQG, for example. This is one of the largest structures ever discovered in the universe. It stretches an unfathomable 4 billion light-years across. To put that into perspective, the Milky Way galaxy is about 100,000 light-years wide. That means this structure is 40,000 times larger than our entire galaxy. If you traveled at the speed of light, it would still take you 4 billion years to get from one end to the other. And that's assuming you could somehow survive the journey through intergalactic space. But why is this such a big deal? Because according to the cosmological principle, nothing in the universe should be larger than about 1.2 billion light-years. That's the so-called homogeneity scale, the size limit where everything should start blending together into a roughly uniform distribution. But the huge LQG is more than 3 times that size. If it's real, and all the data suggests that it is, then our understanding of the large-scale structure of the universe is flawed. And here's where things get even weirder. The huge LQG isn't alone. Other large quasar groups have been discovered, some nearly as large, hinting that these massive structures might be more common than we thought. In fact, there's another even more mysterious object lurking out there, the Hercules Corona Borealis Great Wall. This thing is so enormous that it makes even the huge LQG look small. It spans over 10 billion light-years. That's nearly a tenth of the observable universe. Scientists aren't even sure how to classify it. Some argue it's an even larger LQG, while others say it's an entirely new kind of cosmic structure. But let's take a step back. How do we even detect these structures in the first place? Since quasars are some of the brightest objects in the universe, they're relatively easy to spot with powerful telescopes. Astronomers map their positions in space and look for patterns. When quasars appear to be grouped together in a way that isn't random, it suggests they're part of a larger structure. But here's where things get tricky. Just because we see quasars clustered together doesn't necessarily mean they're physically connected. The universe is vast, and sometimes objects can appear close together simply due to perspective. So how do we know large quasar groups are real? The answer lies in something called redshift. Because the universe is expanding, objects that are farther away from us appear redder due to the Doppler effect. By measuring the redshift of quasars, scientists can determine their distance and confirm whether they truly belong to the same structure. And the data is clear: these objects aren't just coincidentally aligned. They're part of something much bigger. But if LQGs exist, what does that mean for our understanding of the cosmos? One possibility is that the early universe wasn't as uniform as we thought. Maybe certain regions had slightly higher densities, allowing massive structures to form over billions of years. Another possibility is that our model of cosmic evolution is incomplete. Perhaps there are unknown forces or interactions at play that we haven't yet discovered. Some even speculate that LQGs might hint at something far stranger, like variations in the fundamental constants of physics across different parts of the universe. And then there's the wildest theory of them all. What if these structures are evidence of something beyond our universe? Some scientists have proposed that the cosmic web, the vast network of galaxies and dark matter that makes up the large-scale structure of the universe, might extend beyond what we can observe. If that's true, then large quasar groups might not be anomalies at all. They could be glimpses of a much grander, even more complex reality that we're only beginning to understand. Of course, all of this raises even deeper questions. If the universe is structured in ways we don't yet comprehend, what else could be out there? Are there even larger structures waiting to be discovered? Could LQGs be linked to dark matter or dark energy, the mysterious forces that make up most of the cosmos? And perhaps the most mind-bending question of all, could these structures have formed due to unknown physics that challenges everything we think we know? As we continue searching the cosmos, one thing is clear: large quasar groups are a mystery that refuses to be ignored. They challenge our assumptions, defy our models, and hint at a universe that's far more complex than we ever imagined. Maybe, just maybe, they're the key to unlocking secrets that go beyond space and time itself. But let's take a moment to really appreciate how mind-blowing this discovery is. The fact that structures like large quasar groups even exist forces us to rethink one of the most fundamental principles of cosmology: the idea that the universe is roughly the same everywhere when viewed on a large enough scale. If the universe were truly homogeneous, as the cosmological principle suggests, we wouldn't expect to find structures larger than a few billion light years. And yet, here we are, staring at objects that shatter this assumption. And it's not just the size that's baffling, it's the implications. If the universe can organize itself into structures this large, then what else could be out there that we haven't discovered yet? Could there be even bigger formations? Could there be patterns in the cosmos that we don't yet have the tools to detect? Some scientists have even suggested that large quasar groups might be linked to something called the cosmic voids, immense, nearly empty regions of space that appear to be surrounded by filaments of galaxies and dark matter. Think of it like this: imagine the universe as a giant spider web, with galaxies, clusters, and filaments forming the strands, and vast, empty spaces in between. If large quasar groups are concentrated along these cosmic strands, it could mean that the universe has an even deeper, more intricate structure than we ever realized. Some researchers believe that these filaments might even hold clues about dark matter, the invisible substance that makes up most of the universe's mass but has never been directly observed. And this is where things start to get truly bizarre. Some cosmologists have proposed that the distribution of large quasar groups might not be random at all. Instead, they could be arranged in ways that suggest an underlying pattern, one that might point to unknown physical processes at work on an incomprehensible scale. Could the universe itself have a hidden order? Could there be some kind of cosmic architecture that governs how matter is distributed? One radical idea that has emerged from these observations is the possibility that the universe has a preferred direction. This concept, known as cosmic anisotropy, goes against one of the most deeply held assumptions in physics, that the universe looks the same in every direction. If large quasar groups are aligned in a certain way, it could mean that space itself has some kind of directional flow, like a cosmic current stretching across billions of light years. And then there's the even wilder possibility: what if these structures aren't just randomly forming clusters, but are instead evidence of something even more profound? What if they're a sign of ancient cosmic events that shaped the universe as we know it? Some physicists have speculated that the existence of such massive structures could be linked to the early universe's inflationary period, a time of rapid expansion that occurred just fractions of a second after the Big Bang. If certain regions of space expanded at slightly different rates, it might have created variations in density that later led to the formation of these enormous structures. But here's where things get even stranger. Some researchers have pointed out that the distribution of large quasar groups could be hinting at something even more fundamental, a possible connection between the structure of the universe and the mysterious force known as dark energy. Dark energy is the unseen force driving the accelerated expansion of the universe, but its nature remains one of the greatest unsolved mysteries in physics. If large quasar groups are somehow linked to dark energy, it could mean that their distribution isn't just a coincidence. It could be a direct clue about how the universe is evolving on the largest scales. And that brings us to one of the biggest unanswered questions of all. What does this mean for the ultimate fate of the universe? If these massive structures are influencing cosmic expansion, could they eventually cause the universe to evolve in ways we don't yet understand? Could they be affecting the way galaxies form and move? And could they hold the key to predicting what will happen to the cosmos billions or even trillions of years from now? This is where theories start to spiral into some truly mind-bending territory. Some scientists have suggested that if the universe has structures this large, it might mean that our entire cosmic model needs an upgrade. Maybe gravity behaves differently on the largest scales. Maybe the way we calculate distances across the universe isn't as straightforward as we thought. Or maybe, just maybe, there's a deeper, hidden force at work that we haven't even begun to comprehend. And let's not forget one of the most controversial ideas of all, the possibility that large quasar groups could be evidence of a multiverse. If our universe is just one of many, then maybe these massive structures are the result of interactions between different cosmic domains. Some physicists have proposed that if the early universe underwent multiple phases of expansion, it could have created regions of space with different physical properties, some of which might be visible as the giant quasar structures we see today. Of course, this is all highly speculative, but that's what makes this topic so fascinating. The existence of large quasar groups is more than just an astronomical curiosity. It's a direct challenge to our understanding of reality itself. And as we continue to map the universe in greater detail, who knows what else we might discover? One thing is certain, the deeper we look into the cosmos, the more questions we uncover. And large quasar groups are a perfect example of that. They remind us that for all our scientific advancements, we are still just beginning to scratch the surface of the universe's mysteries. But perhaps the biggest question of all is this: if these structures are breaking the limits of what we thought was possible, then what other hidden secrets are still waiting to be found? What else is out there, lurking in the depths of space, waiting to rewrite everything we think we know? The more we study large quasar groups, the more they seem like cosmic anomalies that refuse to fit within our neatly constructed models of the universe. They don't just challenge our assumptions, they outright defy them. And when something in science doesn't make sense, that's usually a sign that we're missing a much bigger piece of the puzzle. One of the biggest puzzles of all is how these massive structures even formed in the first place. Quasars are thought to be powered by supermassive black holes at the centers of galaxies, meaning that wherever we find quasars, we're also seeing some of the most energetic and active regions in the universe. But why do they cluster together into these enormous groups? What force could be strong enough to bind them across distances that should be too vast for gravity to have any significant effect? To put this into perspective, the force of gravity weakens with distance. On the scale of individual galaxies, gravity is strong enough to pull stars into orbits around a central core. On the scale of galaxy clusters, gravity can still hold groups of galaxies together. But when we start talking about distances of billions of light years, the influence of gravity should be negligible. And yet large quasar groups exist, implying that some unseen force or process must be acting over these vast distances to keep them together. Some astrophysicists believe that dark matter might play a role in this, but the problem is that we don't even fully understand what dark matter is. It's an invisible form of matter that doesn't interact with light, and we only know it exists because of the gravitational effects it has on galaxies. But could it also be shaping structures on the scale of large quasar groups? If so, that would suggest dark matter isn't just influencing individual galaxies. It could be guiding the very structure of the cosmos itself. And then there's the possibility that we're looking at something even more exotic. Some researchers have speculated that the distribution of large quasar groups might be revealing hints of a fifth fundamental force of nature. Right now, we recognize four fundamental forces: gravity, electromagnetism, and the strong and weak nuclear forces. But what if there's another, yet undiscovered force that operates only on the largest cosmic scales? Could this be the force that binds these gigantic structures together? This idea, while speculative, isn't entirely out of the question. Scientists have long suspected that there might be hidden forces in the universe that we haven't yet detected. Some theories in physics propose that additional forces could emerge under certain conditions, such as in the early universe or across extreme distances. If large quasar groups are shaped by such a force, it could mean we're on the brink of discovering a completely new aspect of reality. And speaking of new aspects of reality, there's also the possibility that these structures are connected to the concept of the cosmic web, the vast, interconnected network of galaxies, filaments, and voids that make up the large-scale structure of the universe. If large quasar groups are forming along these filaments, then it could mean they are revealing the skeleton of the universe itself. This could help us understand how galaxies form and evolve over billions of years. But it could also open the door to something even more intriguing: the possibility that the universe is structured according to hidden geometric or fractal patterns. Some cosmologists have suggested that the universe might have a fractal-like arrangement, meaning that its structure repeats at different scales. If this is true, then large quasar groups could be one of the largest manifestations of this pattern, a cosmic fingerprint that reveals the underlying order of the universe. Could it be that the laws of physics naturally arrange matter into these enormous, repeating structures? Could the same forces that shape a single galaxy also be responsible for shaping clusters of quasars across billions of light years? And here's where things get even more bizarre. There's a theory that suggests that large quasar groups could be remnants of ancient cosmic strings, hypothetical one-dimensional defects in space-time that might have formed in the early universe. These cosmic strings, if they exist, could be stretching across the cosmos, influencing the formation of galaxies and quasars in ways we don't yet understand. If this theory is correct, then studying large quasar groups could give us a direct link to the physics of the very first moments after the Big Bang. But there's an even bigger question lurking in the background. Are these structures permanent, or are they just temporary arrangements in an ever-changing universe? If we could fast-forward billions of years into the future, would these enormous quasar groups still exist? Or are we simply catching a glimpse of a brief phase in cosmic history? If they do eventually break apart, what would cause that to happen? Would the expansion of the universe stretch them to the point where they dissolve? Or could interactions with dark energy gradually erase their structure? And speaking of dark energy, there's an unsettling idea that some scientists have considered. What if the existence of large quasar groups is a sign that dark energy isn't uniform across the universe? If different regions of space have different amounts of dark energy, that could explain why these massive structures have formed in some places but not others. This would mean that dark energy isn't just pushing the universe apart at a constant rate. It might be shaping the very fabric of space in ways we haven't yet realized. This idea has profound implications for our understanding of the cosmos. If dark energy varies across space, it could mean that the fate of the universe isn't as straightforward as we once thought. Some regions might expand faster than others, leading to vastly different outcomes for different parts of the universe. Could it be that large quasar groups are forming in regions where dark energy is weaker, allowing gravity to hold them together for longer? And if so, could there be other regions of the universe where dark energy is stronger, preventing structures like these from forming at all? The more we investigate these questions, the more it seems like large quasar groups might be one of the biggest cosmic clues we've ever encountered. They challenge our assumptions, force us to rethink the nature of the universe, and hint at forces that we might not even have the tools to detect yet. But perhaps the most exciting thing about them is that they prove just how much we still have to learn. For all of our advances in astronomy and physics, we're still just scratching the surface of understanding the true structure of the universe. And large quasar groups are a perfect example of that. They are like cosmic riddles, daring us to figure out what they mean. Are they simply rare coincidences, or are they telling us something fundamental about the nature of reality? And if we can't yet explain them, what else might be out there, waiting to challenge everything we think we know? If large quasar groups are challenging the very limits of what we know about cosmic structure, then what does that say about the universe itself? Are these massive quasar clusters evidence that the cosmos is more interconnected than we once thought? Or do they hint at an entirely different mechanism at play, one that we have yet to uncover? One of the most perplexing aspects of these structures is their sheer scale. When we look at a single galaxy, we see billions of stars bound together by gravity. When we look at a galaxy cluster, we see hundreds or even thousands of galaxies interacting within a relatively small region of space. But large quasar groups operate on a scale so vast that traditional explanations start to fall apart. They extend for billions of light years, meaning they are comparable in size to some of the largest known structures in the universe. This raises an unsettling question. If these groups exist, could there be even larger structures out there that we simply haven't detected yet? Some researchers believe that large quasar groups could be part of an even more massive cosmic hierarchy, one that goes beyond galaxy clusters and superclusters. If true, this would mean that the universe has levels of structure far beyond what our current models predict. Imagine if galaxies were merely tiny nodes in an immense cosmic lattice, stretching across the universe in patterns too vast for us to comprehend. Could it be that what we see as separate objects, galaxies, quasars, clusters, are actually just small parts of a much greater whole? This idea brings us to one of the biggest mysteries in astrophysics: cosmic voids. These are the massive empty spaces between galaxy clusters, often spanning hundreds of millions of light years. If large quasar groups are arranged in certain patterns, could they be revealing the boundaries of these vast cosmic voids? Could they be outlining the edges of enormous, bubble-like structures in the fabric of the universe? If so, this could change the way we think about cosmic expansion. Traditionally, we've viewed the universe as expanding in a relatively uniform way, driven by dark energy. But what if the expansion isn't uniform at all? What if different regions of space are expanding at different rates, creating zones where matter clusters together more tightly while other regions become emptier over time? If this is the case, large quasar groups could be forming in areas where the expansion is slower, allowing gravity to hold these structures together for much longer than expected. And if the expansion of the universe isn't uniform, then that raises an even bigger question: could the universe itself be anisotropic? In other words, could certain directions in space be fundamentally different from others? If large quasar groups are more common in some parts of the cosmos than in others, that could be evidence that the universe has a preferred direction, something that goes against one of the core assumptions of modern cosmology. The idea that the universe might not be the same in all directions is a radical one, but there is some evidence that points in this direction. Some studies of the cosmic microwave background, the afterglow of the Big Bang, have suggested that there might be subtle patterns in the way the universe expanded in its earliest moments. If large quasar groups are aligned with these patterns, then they could be revealing something fundamental about the nature of space itself. And if that's true, then we might have to reconsider everything we thought we knew about the shape and structure of the universe. Could it be that the cosmos isn't just an expanding bubble of galaxies, but something far more complex? Could there be hidden forces at play, guiding the formation of these massive structures in ways we don't yet understand? One possibility is that these structures are the remnants of something ancient, something that happened in the earliest moments after the Big Bang. Some cosmologists believe that large quasar groups could be the result of density fluctuations in the early universe, frozen into place as the cosmos expanded. If this is true, then studying them could give us a direct glimpse into the physics of the first few moments of existence. But there's another, even more mind-bending possibility. What if these structures are not just shaped by the past, but by something in the future? Some theories in physics suggest that time might not flow in a single direction. Could it be that large quasar groups are being influenced by events that haven't happened yet? Could there be a form of cosmic causality that works both forwards and backwards in time, subtly shaping the structure of the universe in ways we can't yet detect? This might sound like science fiction, but it's not entirely out of the question. Some interpretations of quantum mechanics suggest that time might be more flexible than we realize. And if time itself is connected to the large-scale structure of the universe, then that could mean that these massive quasar groups are more than just random cosmic accidents. They could be the key to understanding time itself. But if that's true, then what else might be out there? If large quasar groups are revealing hidden patterns in the cosmos, could there be other, even stranger structures waiting to be discovered? Could there be regions of the universe where the laws of physics themselves are different? Could these structures be evidence of alternate realities, where the very nature of space and time operates in a way we've never seen before? And then there's the ultimate question: what does all of this mean for us? If the universe is filled with patterns that we don't yet understand, then what role do we play in this vast cosmic puzzle? Are we just tiny observers, trying to make sense of something far beyond our comprehension? Or could it be that our very existence is somehow connected to these massive structures? Some physicists have suggested that consciousness itself might be linked to the fabric of the universe in ways we don't yet understand. Could it be that the patterns we see in the cosmos are not just random, but part of a deeper, underlying structure, one that includes not just galaxies and quasars, but life itself? If so, then studying large quasar groups might not just tell us about the nature of the universe. It might help us understand our own place within it. One thing is certain: the more we learn about these gigantic structures, the more mysterious they become. They challenge our theories, defy our expectations, and force us to confront questions that go beyond physics and into the realm of philosophy. What is the true nature of the cosmos? What forces are shaping it? And could these massive quasar clusters be the first clue in unraveling a reality far deeper than we ever imagined? If large quasar groups are revealing something deeper about the universe, then we have to ask, are they just the tip of the iceberg? Could there be structures out there that make even these colossal formations look small by comparison? When astronomers first discovered superclusters of galaxies, they thought they had found the largest possible structures in the cosmos. But then came the Great Wall, then the Sloan Great Wall, then the Hercules Corona Borealis Great Wall, each one pushing the limits of what we thought was possible. And now, large quasar groups are taking us even further, suggesting that the universe may be structured in ways that defy explanation. One of the most mind-bending ideas in cosmology is that the universe itself might have a hidden architecture, something woven into the very fabric of space-time. What if these enormous quasar clusters are not just random but are part of a grander design, something that we are only beginning to perceive? Could it be that the universe is not a chaotic explosion of matter, but a highly organized system, with these giant structures acting like the cosmic scaffolding that holds everything together? To understand this, we need to look at the fundamental forces that shape the cosmos. Gravity is the most obvious one. It pulls galaxies together into clusters and binds planets to stars. But gravity alone cannot explain why quasars, some of the brightest and most energetic objects in the universe, are clustering on such an unimaginable scale. There must be something else at play, something we haven't yet figured out. One possibility is dark matter, the invisible substance that makes up most of the universe's mass. Could large quasar groups be aligning along vast filaments of dark matter, tracing out the hidden skeleton of the cosmos? Some scientists believe that galaxies and quasars are simply ordinary matter collecting in regions where dark matter has already gathered. If that's true, then studying these quasar groups could be the key to mapping out the structure of the universe's most mysterious ingredient. But there's another possibility. What if these structures aren't just shaped by dark matter, but by something even more elusive, dark energy? While dark matter pulls things together, dark energy pushes them apart, accelerating the expansion of the universe. Could it be that large quasar groups are forming in regions where dark energy behaves differently, creating massive zones where matter accumulates in ways we don't yet understand? If this is true, then these structures could be revealing not just the nature of matter, but the nature of the universe's expansion itself. And that brings us to one of the strangest questions of all. Could these enormous quasar clusters be evidence of something beyond our observable universe? We often assume that what we can see, the galaxies, the quasars, the cosmic background radiation, is all there is. But what if our universe is just a tiny part of a much larger, possibly infinite structure? Could it be that large quasar groups are forming at the boundaries of our observable universe, marking the edges of something even bigger? Some theories suggest that our universe is just one bubble in a vast multiverse, with other universes lying beyond our reach. If that's true, then could these massive quasar structures be connected to those other universes in some way? Could they be the gravitational echoes of other cosmic realms, pressing against the edges of our own? It's an idea that sounds like science fiction, but some physicists believe it might not be so far-fetched. And if that's the case, then we have to rethink everything. What if these massive cosmic structures aren't just forming randomly, but are instead shaped by the unseen influence of other universes? Could there be forces beyond our comprehension tugging at the edges of our reality, subtly shaping the structure of everything we see? If this sounds impossible, consider this. Some of the biggest discoveries in physics have come from noticing patterns that didn't seem to fit our existing theories. The large quasar groups might be just that, a puzzle piece that doesn't quite fit, hinting at a much larger picture. Maybe we've been looking at the universe the wrong way, assuming that space is just an empty void with matter scattered throughout. But what if space itself has structure? What if these massive formations are revealing the hidden geometry of reality itself? Some scientists have suggested that the universe might be shaped like a vast, interconnected web, with galaxies, quasars, and other cosmic structures forming at the intersections of invisible cosmic filaments. If that's the case, then large quasar groups might be marking the points where these filaments converge, like knots in an unimaginably vast cosmic net. But who or what wove that net? Could it be that the laws of physics themselves have a kind of cosmic memory, shaping the universe in ways that go beyond what we currently understand? Some theories suggest that information is fundamental to the nature of reality, that everything we see, from galaxies to atoms, is ultimately just a manifestation of deeper, underlying patterns. If that's true, then large quasar groups might not just be clusters of matter, but the physical expression of something much deeper, a fundamental blueprint that guides the structure of the universe itself. And if that's the case, then what does that say about us? Are we just observers, looking out at a universe far beyond our understanding? Or are we somehow connected to this vast cosmic structure in ways we don't yet realize? One thing is clear: the more we study large quasar groups, the more questions we have. They challenge everything we thought we knew about the universe, forcing us to confront the possibility that reality is far more complex than we ever imagined. And perhaps that's the most exciting part, because every time we think we've reached the limits of our knowledge, the universe has a way of showing us that we're only just beginning to understand the truth. If large quasar groups are revealing something beyond our current understanding, then the next logical step is to ask, what else is out there that we haven't yet noticed? When astronomers first started mapping the universe on large scales, they assumed that cosmic structures would be relatively evenly distributed. Sure, gravity would pull matter into galaxies and clusters, but overall, things should be fairly uniform across the vastness of space. But the discovery of large quasar groups shattered that assumption. They weren't just clusters or superclusters, they were something else entirely. And that raises an even bigger question: are large quasar groups the largest structures in the universe, or are they just the first ones we've found? If they exist, what else might be out there, beyond our ability to detect? Could there be even grander formations, colossal cosmic patterns spanning billions of light years, stretching the very limits of space and time? If so, what could they be made of, and what could they tell us about the universe's deepest secrets? One of the strangest things about large quasar groups is how they challenge the idea that the universe has no preferred direction. According to the cosmological principle, the foundation of modern astrophysics, the universe should look the same in every direction when viewed on a large enough scale. But these structures suggest otherwise. If the universe were truly homogeneous on the largest scales, we shouldn't see clusters of quasars forming into massive structures while other areas remain relatively empty. But we do. That means we have to start questioning whether our understanding of the universe's structure is missing something fundamental. Could there be some deeper force at work, shaping these vast formations in ways we don't yet understand? Some scientists have speculated that the answer might lie in the early moments of the universe itself, specifically, in the way cosmic inflation shaped the fabric of SpaceTime. Inflation is the theory that, in the first fraction of a second after the Big Bang, the universe underwent a period of rapid expansion, stretching space itself at speeds faster than the speed of light. This process would have taken tiny quantum fluctuations, random variations in energy at the smallest scales, and stretched them across the universe, creating the seeds for the cosmic structures we see today. But what if inflation didn't happen the way we think? What if some regions of space expanded differently than others, creating massive zones where matter was more likely to cluster together? If that's the case, then large quasar groups might be relics of this ancient process, fossilized imprints of the universe's birth. And if that's true, then they might not just be telling us about the large-scale structure of the cosmos. They might be revealing clues about the very origins of the universe itself. If inflation created patterns in space that later shaped the formation of galaxies and quasars, then studying these structures could give us insights into the physics of the early universe, physics that we currently can't study in any other way. But there's another, even wilder possibility. What if these massive structures aren't just remnants of the past, but signs of something happening in the universe right now? Some physicists have proposed that space-time itself might not be as static as we assume. Instead of being a smooth, unchanging backdrop, it could be dynamic, evolving, shifting, and even interacting with the matter and energy it contains. Could large quasar groups be evidence of some unknown cosmic process, a sign that the universe is still forming large-scale structures in ways we don't yet understand? One of the biggest mysteries in modern physics is why the universe is expanding at an accelerating rate. The discovery of dark energy, the mysterious force pushing galaxies apart, was one of the biggest surprises in cosmology. But what if dark energy isn't just making the universe expand? What if it's shaping its structure as well? Could these massive quasar formations be regions where dark energy behaves differently, creating zones of increased gravitational attraction or repulsion? If that's the case, then large quasar groups might not just be giant clusters of quasars. They might be signs of a deeper structure in space itself. Some physicists have suggested that dark energy might not be a uniform force, but something more complex, something that varies across the universe. If so, then these quasar groups could be regions where dark energy is interacting with matter in unusual ways, creating massive structures that challenge our current understanding of cosmology. And if that's true, then we have to ask, what does this mean for the future of the universe? If these structures continue to grow, what will they become? Could they merge into even larger formations, shaping the fate of galaxies on a scale we can barely imagine? Or are they signs of something more ominous, evidence that the universe's structure is shifting in ways that could eventually lead to its collapse or transformation? One of the strangest ideas in modern physics is that the universe might have multiple phases. Just like water can exist as a solid, liquid, or gas, space-time itself might have different states. If that's true, then large quasar groups could be forming at the boundaries of these phases, marking the edges of different regions of the universe where the fundamental laws of physics behave in different ways. If we could study them in more detail, we might learn something profound, not just about the universe we see, but about the deeper reality that lies beneath it. At this point, one thing is clear: we are only scratching the surface of what large quasar groups might be. They defy easy explanation, challenging everything from the cosmological principle to our understanding of dark energy. They hint at hidden forces, unseen structures, and possibly even deeper layers of reality that we have yet to uncover. And that's what makes them so exciting, because every time we think we understand the universe, something like this comes along and forces us to think again. So, what's next? How do we study these structures in more detail? Right now, astronomers are using massive surveys of the sky to map out these quasar formations, looking for patterns and anomalies that might give us clues about their origins. Future telescopes, like the James Webb Space Telescope and the next generation of radio observatories, might be able to peer even deeper into space, revealing details we can't yet see. And as our understanding of cosmology advances, new theories might emerge that finally explain why these colossal structures exist, and what they mean for our place in the universe. But for now, large quasar groups remain one of the greatest cosmic mysteries. They are too large to exist under our current theories, yet they are undeniably there. They challenge our understanding of how the universe is structured, hinting at hidden forces and deeper truths waiting to be discovered. And perhaps most importantly, they remind us that the universe is still full of surprises, that no matter how much we think we know, there is always something bigger, stranger, and more mysterious waiting just beyond the limits of our understanding. If large quasar groups are just one piece of the puzzle, what else might be lurking out there, waiting to be discovered? The more we investigate these structures, the more we realize how much we don't know about the universe's largest scales. What if LQGs are just the first hints of something even bigger? One possibility is that these quasar formations are connected to an even grander cosmic web, an underlying structure that spans the entire universe. Astronomers have long suspected that galaxies and clusters form along vast filaments of dark matter, creating a web-like structure that stretches across billions of light years. But could LQGs be revealing a deeper layer of this web, one that we've only just begun to detect? Some scientists believe that if we could map the entire universe in extreme detail, we might find even larger patterns, colossal regions where matter clusters together, forming shapes and structures far beyond our imagination. Imagine entire regions of space where galaxies align into spirals, waves, or even fractal-like patterns, each one shaped by forces we don't yet understand. If large quasar groups are the first signs of these massive formations, then we are on the verge of a discovery that could reshape our understanding of the cosmos. But that raises another question. If these structures exist, why haven't we seen them before? One reason might be the limitations of our current technology. While modern telescopes are incredibly powerful, they can only see so far, and their ability to detect patterns on the largest scales is still developing. Future space observatories, equipped with even more advanced sensors, might reveal details that are currently hidden from view. Another reason might be the way light travels through space. Over billions of years, light from distant quasars can be bent, stretched, and distorted by massive cosmic structures. This means that some of the patterns we see today might not be the original shapes of these formations. If that's the case, then large quasar groups might be even bigger than they appear. Colossal structures stretching across the universe, their true size hidden by the way their light has traveled through space. If this is true, then the implications are staggering. It would mean that the universe isn't just randomly scattered with galaxies and quasars. It has structure on a scale far beyond what we ever imagined. And if there's structure, then there must be rules governing how it forms. What are those rules? Are they the same laws of physics we already know, or is there something more at play? One of the most intriguing possibilities is that these massive structures are influenced by forces we haven't yet discovered. Could there be unknown interactions between galaxies, something beyond gravity and dark matter? Some physicists have suggested that the universe might contain hidden dimensions, extra layers of reality that subtly influence the way matter is distributed on the largest scales. If that's true, then large quasar groups could be the first visible signs of these hidden dimensions, revealing a deeper structure to the cosmos that we've never seen before. And if that's the case, then what else might be out there? If the universe is structured in ways we don't yet understand, could there be even larger formations, superstructures that make large quasar groups look small by comparison? Could there be vast cosmic voids, regions where matter is almost entirely absent, separated by immense walls of galaxies and quasars stretching for billions of light years? Some scientists believe that these massive formations could even hold clues about the fundamental nature of spacetime itself. If the universe has a hidden structure, could it be connected to the way time flows? Could certain regions of the cosmos experience time differently, shaped by the vast patterns of matter and energy that fill them? If so, then large quasar groups might not just be massive structures, they could be windows into the very fabric of reality. But perhaps the biggest mystery of all is what these structures mean for the fate of the universe. If LQGs are part of a larger cosmic web, then what happens to them over time? Will they continue to grow, merging into even larger formations? Or will they eventually break apart, scattered by the expansion of space itself? One possibility is that these structures are temporary, massive but fleeting, destined to dissolve over billions of years. As the universe expands, gravity's grip weakens, and galaxies drift apart. If large quasar groups are held together by gravity alone, then they might eventually be pulled apart, their once massive structures fading into the cosmic background. But what if they don't? What if these structures are stable, locked in place by forces we don't yet understand? Could they be permanent features of the universe, existing for trillions of years, outlasting even the stars themselves? If so, then studying them could give us a glimpse into the far future of the cosmos, revealing the fate of galaxies, the evolution of cosmic structures, and even the ultimate destiny of the universe itself. And that brings us to the biggest question of all: are we seeing the universe as it truly is, or are we only glimpsing part of a much larger reality? If large quasar groups are real, then they are telling us something profound, something that challenges our deepest assumptions about the cosmos. They are showing us that the universe is structured in ways we never expected, shaped by forces we don't yet understand. So what happens next? The search continues. Astronomers are mapping more of the sky, searching for even larger structures, looking for patterns that might reveal the true nature of these colossal formations. The next generation of telescopes will push our understanding even further, scanning the universe in greater detail than ever before. And as our technology improves, we may finally uncover the truth behind these mysterious formations, unlocking secrets that have been hidden in the cosmos for billions of years. For now, large quasar groups remain one of the greatest cosmic enigmas. They challenge everything we thought we knew about the universe. They hint at forces and structures far beyond our current understanding. And they remind us that, no matter how much we discover, the universe will always have more mysteries waiting to be explored. If large quasar groups are just the beginning, what other structures might be hiding in the depths of space? Could there be formations so massive that we haven't even developed the technology to detect them yet? Some scientists believe that if we continue to map the universe at larger and larger scales, we might uncover something even more profound, a structure so enormous that it forces us to rethink everything we thought we knew about cosmic evolution. The biggest problem we face is that the farther we look into space, the harder it becomes to make sense of what we're seeing. Light from distant objects has been traveling for billions of years, which means we're not just looking across space, we're looking back in time. This makes it difficult to know whether the large quasar groups we observe today are still structured in the same way, or if they have changed over time. Some of them might not even exist anymore in their current form. This also raises another question. If we're seeing these massive structures from the past, does that mean there were even larger formations before them? What if, billions of years ago, the universe contained even greater structures, colossal networks of quasars, galaxies, and dark matter that have since dispersed? And if these structures existed in the past, could we still find evidence of them today? Some researchers have proposed that remnants of these ancient cosmic formations might still be detectable as strange distortions in the cosmic microwave background, the faint radiation left over from the Big Bang. If large quasar groups are part of a larger, hidden structure, then they might have left imprints in this radiation, tiny fluctuations that could reveal the true scale of these formations. But what if the key to understanding LQGs isn't just about mapping space? What if the answer lies in something even more fundamental, the nature of reality itself? Some physicists believe that these massive cosmic structures could be evidence of new physics, hidden dimensions, or even parallel universes. One idea suggests that large quasar groups might not just be collections of galaxies. They could be intersections between different regions of the universe, areas where space itself is structured differently. If this is true, then these formations might not follow the same physical laws as the rest of the cosmos. They might be shaped by unknown forces, operating on a scale that we haven't yet begun to understand. Another theory suggests that the universe might be much larger than we think, and that large quasar groups are just small pieces of an even grander cosmic pattern. If the observable universe is just a fraction of a much larger whole, then what we see as separate LQGs might actually be part of a continuous structure that extends far beyond our current field of view. This would mean that the true size of these formations is even greater than we can currently measure, spanning distances beyond anything we've ever imagined. If that's the case, then our entire understanding of cosmic evolution might need to be rewritten. The standard model of cosmology assumes that matter is evenly distributed at the largest scales. But if LQGs are real, then they suggest that the universe has structure on scales far larger than we expected. This could mean that gravity behaves differently at extreme distances, or that some unknown force is shaping the distribution of matter in ways we don't yet understand. Some scientists have even speculated that these massive formations could be evidence of interactions between different universes. If our universe is part of a larger multiverse, then these structures might be the points where different regions of reality intersect, zones where matter clusters in unusual ways due to the influence of other dimensions. If this idea is correct, then large quasar groups could be the first visible signs of a much deeper cosmic connection, one that links our universe to others beyond our own. And that leads to an even more mind-bending question. If LQGs are part of a larger structure, then what is that structure leading to? Could there be something even bigger, something beyond even the largest known quasar groups? Could we be seeing only the first hints of a vast cosmic architecture, one that stretches across the entire universe and beyond? If such a structure exists, then its implications would be staggering. It could mean that the universe is not just a collection of galaxies scattered across space, but something much more ordered, something designed, or at the very least, something governed by principles we don't yet understand. It could mean that the universe has a shape, a form, a pattern that extends beyond our ability to perceive. Some have even suggested that these vast cosmic formations might hold clues about the ultimate fate of the universe. If LQGs are stable, then they could persist for trillions of years, remaining long after stars have burned out and galaxies have faded away. If they are connected to a deeper structure, then they might reveal the long-term evolution of the cosmos, showing us how matter is distributed at the grandest scales over immense stretches of time. But what if these structures are not permanent? What if, as the universe continues to expand, they begin to break apart? If that happens, then large quasar groups might only be temporary features of the cosmos, existing for a brief period before being stretched beyond recognition. If that's the case, then we may be living in a special time in the history of the universe, a time when these structures are still visible, but before they fade away forever. This brings us to one of the most important questions in all of cosmology. Is the universe static, or is it evolving in ways we don't yet understand? If LQGs are part of a larger pattern, then that pattern might be changing over time, shaping the universe in ways we can only begin to guess. If so, then studying these structures isn't just about understanding the past, it's about predicting the future, unlocking the secrets of cosmic evolution, and discovering what will happen to the universe in the eons to come. And that's what makes large quasar groups one of the greatest space mysteries of all time. They challenge everything we thought we knew about the cosmos. They hint at structures beyond our comprehension. They force us to ask questions that go beyond physics, beyond astronomy, and into the very nature of reality itself. What are these formations? How did they come to be? And what do they mean for the future of the universe? These are the questions that scientists are still trying to answer. And as our technology improves, as our understanding deepens, we may finally unlock the truth behind these colossal cosmic structures, unraveling one of the greatest mysteries the universe has ever presented. Large quasar groups, LQGs, remain one of the most perplexing and controversial cosmic structures ever discovered. They challenge the very foundation of modern cosmology, which assumes that the universe is homogeneous on the largest scales. If structures like LQGs exist at distances spanning billions of light-years, does this mean our current understanding of the universe's large-scale structure is incomplete? What if the distribution of matter is far less random than we once believed? One of the most striking aspects of LQGs is their sheer scale. The largest known LQG, the huge Large Quasar Group, huge LQG, spans approximately 4 billion light-years across. To put that into perspective, our entire Milky Way galaxy is about 100,000 light-years wide, meaning this single quasar group is tens of thousands of times larger than our entire galaxy. The implications of such vast structures are staggering. But how did these formations come to exist? Cosmologists believe that the early universe was a dense and relatively uniform soup of particles. Over time, slight variations in density caused matter to clump together under the influence of gravity, forming the first galaxies. If LQGs are real, they suggest that some regions of the universe had much larger density fluctuations than previously thought, fluctuations so extreme that they led to the formation of massive, interconnected quasar systems. However, this presents a major problem. According to the standard model of cosmology, there is a theoretical limit to how large cosmic structures can be. This is known as the cosmological principle, which states that when you look at the universe on sufficiently large scales, matter should appear to be evenly distributed. The existence of LQGs defies this principle. They suggest that the universe has structure on scales far larger than what should be possible. Could LQGs be remnants of an even grander cosmic web? Some researchers speculate that these quasar groups might be part of a larger, hidden pattern, perhaps the early scaffolding upon which galaxies formed. If this is true, then it raises another question: are there even larger structures waiting to be discovered? Could we find formations stretching across tens of billions of light years, connecting entire regions of the cosmos? To answer these questions, scientists have turned to detailed simulations of the early universe. Using supercomputers, researchers have attempted to recreate the conditions that might give rise to LQGs. These simulations suggest that such massive structures could form if certain conditions in the early universe were different from what we currently assume. If the laws of physics varied slightly at cosmic scales, or if dark matter behaved differently in the past, then the formation of LQGs might not be as impossible as we once thought. Another possibility is that LQGs are evidence of a much more interconnected universe, one where galaxies and quasars are linked by filaments of dark matter stretching across unimaginable distances. This idea aligns with what is known as the cosmic web, a vast network of filaments made up of galaxies, gas, and dark matter. If LQGs are just denser clusters within this web, then they could be revealing something fundamental about how matter organizes itself in the universe. But what if there's something even stranger going on? Some physicists have proposed that LQGs might be evidence of unknown forces shaping the universe. If gravity behaves differently on extremely large scales, then our understanding of cosmic evolution might be incomplete. Some theories suggest that a new force, something beyond the four fundamental forces we currently know, could be influencing the way galaxies and quasars cluster together. Could LQGs be the result of hidden dimensions? Some versions of string theory propose that additional dimensions beyond the familiar three of space and one of time could have subtle effects on cosmic structure. If these hidden dimensions influence how matter clumps together, then perhaps LQGs are a sign of deeper, unseen layers of reality shaping the universe. Another radical possibility is that LQGs might be relics of a previous cosmic cycle. Some theories propose that the universe undergoes an endless cycle of expansion and contraction, known as the Big Bounce. If this is true, then LQGs could be the remains of structures that existed in a previous version of the universe, carried over in some unknown way into our current cosmic epoch. And then there's the possibility that LQGs are connected to something even more mind-bending: parallel universes. Some cosmologists speculate that the universe we see is just one of many, and that LQGs might be places where different realities intersect. If multiple universes interact in some way, then these massive structures could be the result of gravitational influences beyond our own universe. Could LQGs be the first observable evidence that our cosmos is part of a vast multiverse? If so, studying them could give us clues about what lies beyond the limits of our observable universe. If they are anomalies in the cosmic fabric, they might hint at exotic physics, unknown particles, or even new forces that extend beyond our current understanding of the universe. The biggest challenge in solving the mystery of LQGs is that they are incredibly far away. The light from these quasars has traveled for billions of years to reach us, meaning we are looking deep into the past. Because of this, it's difficult to determine whether these structures are still intact today, or if they have changed over time. If LQGs have evolved, then studying them might reveal something about the long-term fate of cosmic structures, whether they remain stable, collapse, or disperse as the universe expands. One thing is certain: large quasar groups challenge our understanding of the universe in ways that few other discoveries have. They push the boundaries of what we thought was possible, forcing us to rethink fundamental principles of cosmology. Whether they are part of a larger cosmic web, relics of a previous universe, or even signs of unknown physics, LQGs represent one of the greatest space mysteries we have ever encountered. As new telescopes come online, such as the James Webb Space Telescope and future deep space observatories, we may finally get closer to answering the questions surrounding LQGs. Are they truly the largest structures in the universe? Or are they just the first glimpse of something even bigger, something that could change our entire understanding of reality? The search for answers continues. And as we look deeper into the cosmos, one thing becomes clear: the universe is far more mysterious, far more complex, and far more extraordinary than we ever imagined. Large Quasar Groups, LQGs, remain one of the most baffling and controversial cosmic phenomena ever discovered, defying our understanding of the large-scale structure of the universe. Their sheer size alone raises fundamental questions about whether the universe follows the standard cosmological principles we assume it does. If these immense formations exist, what else could be out there? Could there be even larger, yet undiscovered structures that completely overturn what we think we know about the cosmos? One of the most perplexing aspects of LQGs is how they seemingly violate the cosmological principle, which suggests that matter should be evenly distributed when viewed on a sufficiently large scale. But if structures as vast as LQGs exist, then perhaps the universe isn't as uniform as we once thought. The discovery of the huge LQG, which spans about 4 billion light-years across, was a major shock to the scientific community because it contradicts the theoretical limits for cosmic structures. This forces us to rethink how galaxies, black holes, and cosmic matter have formed and evolved over billions of years. But the question remains: how do these vast cosmic structures form in the first place? The standard model of cosmology suggests that after the Big Bang, tiny quantum fluctuations in the early universe gradually grew into the large-scale structures we see today, forming galaxies, galaxy clusters, and filaments of the cosmic web. But the existence of LQGs suggests that some regions of the universe experience much larger density fluctuations than we expected, leading to the formation of these enormous quasar clusters. Quasars themselves are fascinating objects, supermassive black holes at the centers of galaxies that consume vast amounts of matter, emitting intense radiation in the process. Because LQGs are composed of numerous quasars, their existence suggests that these black holes might be more interconnected than we realize. Could LQGs be signs of an even greater underlying structure, perhaps a vast network of black holes connected across billions of light-years? Some researchers have speculated that these formations may represent the early scaffolding of the universe, a framework upon which galaxies and other structures formed over time. This raises another mystery. If LQGs are real, then what other undiscovered cosmic megastructures might be out there? Could there be formations stretching across tens of billions of light-years, linking entire regions of the universe in ways we don't yet understand? Some cosmologists believe that LQGs could be part of an even larger hidden pattern, hinting at the existence of structures that are currently beyond our observational reach. To investigate this, scientists have turned to advanced computer simulations to model how such massive structures could have formed. Using powerful supercomputers, they have attempted to recreate the conditions of the early universe, simulating the growth of galaxies and quasars over billions of years. These simulations suggest that if certain conditions were slightly different, such as variations in dark matter behavior or differences in how gravity operates on extreme scales, then the formation of LQGs might not be as impossible as we once thought. Dark matter itself plays a crucial role in this puzzle. It is widely believed that dark matter forms the backbone of the cosmic web, with galaxies and clusters accumulating along its filaments. If LQGs are simply denser regions of this web, then they could be revealing something fundamental about how matter is distributed in the universe. Some scientists speculate that LQGs might be regions where dark matter is unusually concentrated, possibly influencing the growth of galaxies and black holes in unexpected ways. But what if something even stranger is at play? Some radical theories suggest that LQGs might be evidence of unknown forces influencing cosmic evolution. If gravity behaves differently on extremely large scales, then our entire framework for understanding the universe might need to be revised. Some alternative theories propose that a fifth fundamental force, beyond gravity, electromagnetism, and the nuclear forces, could be shaping the distribution of galaxies on vast scales. If such a force exists, It could explain why LQGs defy our current understanding of cosmic structure formation. And then there's the possibility that LQGs are evidence of hidden dimensions. Some versions of string theory propose that additional dimensions beyond our familiar 3 of space and 1 of time could subtly affect the way matter clusters in the universe. If these hidden dimensions influence the behavior of gravity or dark matter, then LQGs might be one of the first observable hints of an unseen, extra-dimensional reality shaping our cosmos. Another intriguing idea is that LQGs might be remnants of an earlier cosmic epoch. Some cosmological theories propose that the universe undergoes cycles of expansion and contraction, a process known as the Big Bounce. If this is true, then perhaps LQGs are leftover structures from a previous version of the universe, persisting across cosmic cycles in a way we don't yet understand. And what if LQGs are more than just large-scale structures? Could they be connected to something even more mysterious, like the concept of parallel universes? Some physicists speculate that the universe we observe is just one of many, and that LQGs might be places where different realities intersect. If multiple universes have gravitational interactions with one another, then these massive structures could be a sign of cosmic forces extending beyond our own observable universe. If LQGs truly are anomalies in the cosmic fabric, then they could be revealing something far deeper, something that challenges the very nature of reality itself. Are they simply dense clusters of quasars, or do they point to a fundamental flaw in our understanding of the universe? If they are part of an even grander structure, they might suggest that the universe has a hidden order on scales far beyond what we can currently detect. One of the biggest challenges in studying LQGs is their immense distance from us. Because they are billions of light years away, we are observing them as they existed in the distant past. This means that we don't know for sure whether these structures are still intact today, or if they have changed over time. If they have evolved in ways we don't expect, then studying them could reveal important clues about the long-term fate of cosmic structures, whether they remain stable, collapse, or disperse as the universe expands. As astronomers continue to refine their models and gather more observational data, LQGs remain one of the greatest cosmic mysteries. They defy our assumptions about how the universe is structured, challenging long-held theories and forcing us to consider possibilities we never imagined. Whether they turn out to be the largest structures in the universe or just the first hints of something even bigger, one thing is certain. LQGs remind us that the cosmos is far more complex, far more mysterious, and far more fascinating than we ever thought possible. With new telescopes coming online, such as the James Webb Space Telescope and upcoming deep space observatories, we may finally get closer to answering the questions surrounding LQGs. Will future discoveries confirm that these structures are anomalies? Or will they reveal that the universe is structured in ways we never anticipated? Could there be even larger formations out there, waiting to be uncovered? The deeper we look into the cosmos, the more we realize just how little we truly understand. And that's what makes space so thrilling. It is full of mysteries waiting to be solved. LQGs are just one piece of the puzzle, but they might be the key to unlocking a whole new understanding of the universe itself. Large Quasar Groups, LQGs, are more than just collections of ancient quasars. They are cosmic anomalies that challenge the very fabric of modern astrophysics. Their sheer scale defies the long-held assumption that the universe becomes more homogeneous at larger scales. If LQGs exist, then something fundamental about our understanding of structure formation is incomplete. But what exactly could explain their existence? Could they be relics of a primordial era when the universe was vastly different from today? Or could they be evidence of an entirely new cosmic force, something that we have yet to discover? One of the key issues with LQGs is the theoretical limit imposed by the cosmological principle, which suggests that structures larger than 1.2 billion light-years should not exist. Yet, here we have the huge LQG, spanning a staggering 4 billion light-years, making it one of the largest known structures in the observable universe. If such an entity exists, then the fundamental assumption that the universe is uniform at large scales must be reconsidered. This could mean that either our models of cosmic evolution are incorrect or that there are unknown interactions taking place on vast scales that we do not yet understand. A possible explanation for the existence of LQGs lies in the early universe, where small fluctuations in the density of matter were amplified by gravitational attraction. Over billions of years, these fluctuations grew into galaxies, clusters, and eventually the cosmic web. However, the presence of LQGs suggests that some regions of the universe must have experienced far greater density variations than our models predict. This implies that the early universe may have been far more chaotic and structured than we previously believed. One idea is that these structures are shaped by the behavior of dark matter. Dark matter is thought to be the invisible scaffolding that holds the universe together, influencing the motion of galaxies and forming the cosmic web. If LQGs are regions where dark matter is unusually concentrated, they might provide new insights into how this mysterious substance behaves on extremely large scales. Some scientists speculate that dark matter itself might have different properties in different regions of the universe, which could explain why LQGs appear where they do. Another intriguing possibility is that LQGs are remnants of an ancient phase transition in the universe's history. Much like water turning into ice, the universe may have undergone dramatic shifts in its structure as it expanded and cooled. If an early phase transition caused certain regions to become denser than others, then the formation of LQGs might be a direct consequence of these early cosmic conditions. If true, studying them could reveal important details about how the universe transitioned from its hot, dense beginning to the vast cosmos we see today. But what if LQGs aren't just large-scale structures? What if they hint at something even more profound, such as hidden dimensions or alternative physics? Some versions of string theory suggest that our universe may contain additional dimensions beyond the familiar three of space and one of time. If these extra dimensions influence the way matter clumps together, then LQGs might be the first observable evidence of an unseen, higher dimensional reality. This could mean that the fundamental forces we experience, gravity, electromagnetism, and nuclear forces, are only part of a much larger framework governing the cosmos. And then there's the possibility that LQGs are not anomalies at all but rather the first hints of an even grander structure spanning the universe. If these groups of quasars are interconnected in ways we do not yet understand, they might be part of a much larger network of galaxies, black holes, and cosmic filaments stretching across billions of light years. Could LQGs be the visible fragments of a vast, hidden framework that underlies the entire cosmos? If so, then we are only beginning to grasp the true nature of the universe's architecture. One of the most significant questions surrounding LQGs is whether they are still intact today. Since they are billions of light years away, we are observing them as they existed in the distant past. Have they remained stable over time, or have they broken apart due to cosmic expansion? If future observations reveal that LQGs are dispersing, it could provide crucial insights into how large-scale structures evolve over time. If, on the other hand, they have remained intact, then it would raise even more questions about the forces holding them together. New telescopes and observational techniques are providing astronomers with better tools to study LQGs. The James Webb Space Telescope, for example, is capable of peering deeper into the universe than ever before, potentially revealing new details about the quasars that make up these enormous structures. Future projects, such as the Square Kilometre Array, SKA, will allow scientists to map the large-scale structure of the universe with unprecedented precision. These advancements could help determine whether LQGs are truly unique, or if they are part of a much broader pattern of cosmic organization. Ultimately, the study of LQGs forces us to confront one of the most fundamental questions in cosmology. Is the universe truly random, or is there an underlying order we have yet to uncover? If LQGs are part of a larger, hidden structure, then they could provide a key to unlocking deeper cosmic truths. Perhaps they are evidence of unknown physical laws shaping the universe on unimaginable scales. Perhaps they are remnants of an earlier cosmic epoch, revealing a past universe vastly different from the one we inhabit today. As research continues, LQGs will remain one of the most perplexing mysteries in astrophysics. They challenge the assumptions we have held for decades and push us to explore new frontiers in our understanding of the cosmos. Whether they turn out to be cosmic anomalies, relics of the early universe, or something even more astonishing, one thing is certain: They remind us of just how much we still have to learn about the vast and mysterious universe we call home. The mystery of large quasar groups extends beyond their mere existence. It challenges the very nature of how matter organizes itself across the vast cosmic landscape. If the universe truly obeys the cosmological principle, then structures beyond a certain scale should not exist. Yet, LQGs defy this assumption, forcing scientists to reconsider what they thought they knew about the large-scale structure of the universe. One of the most pressing questions is, how did LQGs form in the first place? The standard model of cosmology suggests that matter in the universe is distributed in a relatively uniform way when viewed on the largest scales. Small-scale structures like galaxies and galaxy clusters are expected, but massive formations spanning billions of light-years should be impossible under our current understanding. This raises the possibility that something unusual happened in the early universe, perhaps an unknown force, an exotic form of matter, or an ancient cosmic event shaped these structures in ways we have yet to comprehend. Some scientists speculate that the presence of LQGs may be linked to the mysterious nature of dark energy, the force responsible for the accelerating expansion of the universe. If dark energy behaves differently in certain regions of the cosmos, it could influence the way galaxies and quasars clump together. Perhaps LQGs are regions where dark energy's effects were weaker, allowing quasars to remain more tightly bound than expected. This could mean that the very fabric of space itself varies across different regions of the universe, a possibility that would have profound implications for our understanding of physics. Another explanation for LQGs could involve cosmic inflation, the rapid expansion of the universe that occurred just moments after the Big Bang. If inflation was not perfectly uniform, then certain regions of the universe may have experienced different rates of expansion, leading to the formation of large-scale structures like LQGs. In this scenario, LQGs would be direct evidence of inflationary fluctuations that shaped the universe billions of years ago. By studying these structures, scientists might be able to learn more about the conditions that existed in the first moments after the Big Bang. But what if LQGs are not anomalies at all? What if they are simply the visible portions of an even larger structure? Some theories suggest that the universe may be structured in a way that we do not yet fully understand. If there are patterns or hidden connections linking LQGs to other cosmic structures, then we may be looking at just one piece of a much greater puzzle. Could these quasar groups be part of a massive cosmic network that extends beyond our current observational limits? If so, then the universe may be far more interconnected than we ever imagined. Another perspective is that LQGs could be a sign of an entirely new kind of physics, something that does not fit within the framework of general relativity and the standard model of cosmology. Perhaps there are hidden variables influencing the distribution of matter on vast scales. Could exotic particles, unknown cosmic forces, or even higher dimensional influences be playing a role in the formation of these structures? If LQGs turn out to be the first evidence of a new physical phenomenon, they could revolutionize our understanding of how the universe works. One of the greatest challenges in studying LQGs is their immense distance from Earth. Because light from these quasars has taken billions of years to reach us, we are seeing them as they existed in the distant past. This means that they might have evolved or even dispersed over time. If future observations reveal that LQGs have broken apart, it could indicate that they were only temporary structures, held together by conditions that no longer exist. However, if they remain intact, it would suggest that they are bound by forces strong enough to resist the expansion of the universe. New observational techniques are allowing scientists to probe deeper into the structure of LQGs than ever before. Advances in radio astronomy, infrared imaging, and gravitational lensing provide new ways to map out these colossal formations. The upcoming Square Kilometre Array, SKA, will be capable of detecting faint radio signals from distant galaxies, potentially uncovering new details about the nature of LQGs. Meanwhile, deep space telescopes like the James Webb Space Telescope are helping astronomers analyze the individual quasars that make up these groups, revealing clues about their origins and evolution. Despite all of these efforts, many fundamental questions remain unanswered. Do LQGs represent an early stage in the evolution of the cosmic web, or are they unique structures that do not fit within our current models? Are they evidence of unknown physical laws, or are they simply statistical anomalies that will disappear with further observations? Could they be connected to dark matter, dark energy, or some other unknown component of the universe? Perhaps the most mind-bending possibility is that LQGs are remnants of an entirely different kind of universe, one that existed before the Big Bang. Some speculative theories propose that the universe undergoes cycles of expansion and contraction, with each cycle leaving behind traces in the cosmic landscape. If LQGs are ancient relics of a previous cosmic era, then studying them could provide insights into the nature of time itself. No matter what the ultimate explanation turns out to be, one thing is clear: large quasar groups challenge our understanding of the universe in ways that few other discoveries do. They force us to question our assumptions, rethink fundamental principles, and explore the unknown. As new data continues to emerge, we may find that LQGs are just the beginning of a much larger and deeper cosmic mystery, one that will reshape our understanding of the cosmos for generations to come. If large quasar groups are more than just statistical anomalies, then their existence could imply that the cosmic web, the vast structure of galaxies and dark matter stretching across the universe, is not as random as we once thought. Instead of a universe where matter is evenly distributed over vast distances, LQGs suggest that something is guiding or influencing the formation of galaxies on an enormous scale. This could point to hidden cosmic forces, unexplored aspects of dark matter, or even a radical rethinking of the laws that govern structure formation in the universe. One of the strangest implications of LQGs is their potential link to the cosmic horizon problem. The observable universe is limited by how far light has traveled since the Big Bang, meaning there is a maximum distance beyond which we cannot see. If LQGs extend beyond this boundary, it raises questions about whether the universe is structured in ways we cannot currently detect. Could these formations be part of an even larger hidden framework that extends beyond our observational limits? Some scientists speculate that we may only be seeing pieces of an intergalactic lattice, with connections that stretch far beyond our ability to measure. Another possibility is that LQGs are shaped by exotic forms of matter or energy that do not interact with light in the same way as ordinary matter. Dark matter, for instance, makes up most of the universe's mass, yet it remains invisible to telescopes. If LQGs are somehow tied to variations in the density of dark matter, they could be revealing hidden structures that exist on scales much larger than previously thought. In this scenario, LQGs may be acting as cosmic markers, highlighting regions of the universe where dark matter clump together in ways that defy our current models. Some researchers even propose that LQGs might be linked to cosmic voids, the vast, empty regions of space between galaxy clusters. If these quasar groups formed in areas where matter was unusually dense, then their existence could suggest that the universe has a far more complex distribution of mass than standard theories predict. These voids and LQGs may be two sides of the same coin, representing an intricate balance between matter and emptiness across the universe. If true, this could revolutionize our understanding of how galaxies and cosmic structures emerged from the chaotic conditions of the early universe. Then there's the question of whether LQGs could be indicators of a deeper, hidden order within the cosmos. Some physicists believe that the laws of physics themselves may not be uniform across the universe. If the fundamental forces that shape matter vary in different regions of space, it could explain why LQGs have formed in certain areas but not others. This idea is highly controversial, as it challenges one of the core assumptions of modern cosmology, that the universe is governed by the same laws everywhere. However, if evidence continues to support the existence of structures larger than theoretically possible, scientists may have no choice but to consider the possibility that physics itself changes across the cosmos. An even more radical idea is that LQGs could be evidence of interactions between our universe and other universes. In some versions of the multiverse theory, different universes may collide or influence each other in subtle ways. If another universe left an imprint on our own billions of years ago, it could have altered the distribution of matter in ways that led to the formation of these massive structures. While this is highly speculative, it offers an intriguing possibility. LQGs may be the first observable clues that our universe is not alone. Another challenge in studying LQGs is that they are so far away that we are seeing them as they existed billions of years ago. If we could somehow observe these quasar groups as they are today, would they still exist in the same form? If they have since dispersed, it might indicate that they were only temporary features, bound together by early universe conditions that no longer exist. On the other hand, if they remain intact, it would suggest that LQGs are held together by unknown forces capable of resisting the expansion of the universe. As technology advances, astronomers are finding better ways to study LQGs and their properties. The James Webb Space Telescope is providing unprecedented views of distant quasars, allowing scientists to analyze their distribution in greater detail. Upcoming observatories like the Square Kilometer Array will be able to detect faint radio emissions from these distant objects, potentially revealing new insights into their structure and formation. By mapping out LQGs in even greater detail, researchers hope to determine whether they are truly anomalies or part of a larger, unseen cosmic pattern. But the biggest question remains: what does the existence of LQGs mean for our understanding of the universe? If these massive structures should not exist according to our current theories, then what else are we missing? Are there even larger formations waiting to be discovered? Could the universe itself be structured in ways that we have yet to comprehend? LQGs force us to confront the possibility that the cosmos is far more complex than we ever imagined. They challenge the limits of our knowledge, pushing us to reconsider the very foundations of modern astrophysics. Whether they are anomalies, remnants of a hidden cosmic order, or signs of an undiscovered force, one thing is certain: their mystery is only just beginning to unfold. If large quasar groups represent something more than just statistical oddities, then we must rethink the very fabric of the cosmos. The scale at which these structures exist forces us to ask: are the fundamental laws of physics as universal as we believe? One of the key assumptions in cosmology is the cosmological principle, which states that on large enough scales, the universe is homogeneous and isotropic, meaning it looks roughly the same in every direction. But LQGs seem to challenge this assumption. If structures larger than the theoretical limit exist, it could mean that matter in the universe is not distributed as evenly as we thought. This would have profound consequences for models of cosmic evolution, potentially requiring a complete overhaul of how we understand the large-scale structure of space. To truly grasp the implications of LQGs, we need to look at how galaxies form and organize themselves. Standard models suggest that galaxies cluster together due to gravitational attraction, forming structures like filaments, walls, and voids in the cosmic web. These formations are shaped by the distribution of dark matter, which acts as a cosmic scaffolding, pulling ordinary matter into clusters over billions of years. But if LQGs are stretching across distances that exceed this predicted structure, then something else must be influencing their formation. One possible explanation involves the initial conditions of the universe. The cosmic microwave background radiation, essentially the leftover heat from the Big Bang, contains tiny fluctuations that later grew into the galaxies and galaxy clusters we see today. Some scientists speculate that these fluctuations may not have been as random as we think. Instead, there may have been pre-existing structures or influences that determined where matter would cluster, resulting in the formation of massive structures like LQGs. Another possibility is that LQGs are remnants of cosmic strings, hypothetical defects in space-time that may have formed during the early universe. These cosmic strings, if they exist, could act as gravitational attractors, pulling matter into long, thread-like structures over billions of years. If LQGs are aligned with such cosmic strings, they could represent a deeper, hidden structure in the universe that we have yet to fully understand. Some researchers have proposed that LQGs might be linked to the expansion of the universe itself. The universe has been expanding since the Big Bang, and this expansion is accelerating due to the mysterious force known as dark energy. If dark energy has not been uniform throughout cosmic history, then certain regions of space might have expanded at different rates. This could have led to the formation of massive quasar clusters in some areas while leaving other regions emptier than expected. In this scenario, LQGs could be signposts of variations in dark energy, providing clues about the true nature of this elusive force. But what if LQGs are not just cosmic accidents? Some scientists entertain the idea that these massive structures could be artificial in nature, perhaps the result of unknown cosmic-scale processes that we do not yet understand. If advanced civilizations exist on an intergalactic scale, could they have manipulated quasars or galaxy clusters in ways that left behind observable traces? While this idea may seem far-fetched, it is not entirely outside the realm of possibility. If intelligent life exists beyond Earth, we have no idea what kind of engineering feats it might be capable of. LQGs could be an unintended byproduct of large-scale cosmic phenomena that go beyond natural astrophysical processes. Even if we assume LQGs are entirely natural formations, their presence forces us to reconsider the ultimate fate of the universe. If these structures persist for billions of years, then their gravitational influence could shape the evolution of galaxies in ways we have yet to predict. Could LQGs be precursors to even larger structures? Are they forming supercluster highways that might one day merge into even more massive configurations? If so, then the universe might not be headed toward uniformity, but rather toward a future where matter becomes increasingly concentrated into massive, interconnected structures. To test these ideas, astronomers continue to search for more LQGs. The discovery of additional groups similar to the huge LQG or the Claus-Campusano LQG would provide valuable data about their distribution and possible formation mechanisms. If we find that LQGs are more common than previously believed, it could mean that our understanding of cosmic structure is fundamentally incomplete. On the other hand, if LQGs turn out to be rare anomalies, we will need to investigate what unique conditions allowed them to form in the first place. Future missions, such as the Euclid Space Telescope and the Vera C. Rubin Observatory, will help map the large-scale structure of the universe with unprecedented detail. These telescopes will not only detect more quasars but also analyze their spatial arrangement, allowing scientists to determine whether LQGs are isolated events or part of a broader cosmic pattern. With these new tools, we may finally be able to answer the questions that LQGs raise. But the mystery does not stop there. If LQGs are challenging our understanding of cosmic structure, then what else are we missing? Could there be even larger formations waiting to be discovered, structures that completely rewrite the rules of astrophysics? Some astronomers speculate that beyond LQGs, there may be hyperclusters, even larger regions of galaxy groups that extend across unimaginable distances. If such formations exist, then our universe is structured on a scale that we have barely begun to comprehend. The study of LQGs is not just about understanding quasars or galaxy clusters, it is about questioning the very nature of reality itself. These structures defy expectations, suggesting that the universe may not be as uniform or predictable as we once believed. They challenge our assumptions, push the limits of our knowledge, and force us to confront the possibility that there are forces at work that we have yet to discover. As we continue to explore these enigmatic formations, one thing is certain: the universe still holds many secrets, and LQGs are just one of the many mysteries that remind us of how much we have yet to learn. Whether they are relics of the early universe, signs of new physics, or something else entirely, they stand as cosmic beacons, challenging us to look deeper, think bigger, and question everything we thought we knew about the vast expanse of space. The existence of large quasar groups, LQGs, forces us to reconsider the way we model the universe. If these structures truly exceed the theoretical size limit imposed by the cosmological principle, then either our current understanding of cosmic structure formation is incomplete, or we need to rethink the fundamental rules that govern the large-scale distribution of matter. This isn't just a minor adjustment in our understanding, it's a potential paradigm shift that could impact everything from the way we simulate the early universe to how we predict the fate of cosmic expansion. One of the biggest questions surrounding LQGs is how they formed. Standard astrophysical models rely on the idea that matter clumps together over billions of years due to gravitational attraction, forming structures like galaxies, clusters, and superclusters. However, the existence of structures like the huge LQG, which spans over 4 billion light-years, suggests that these formations are either the result of unknown cosmic processes or they formed much earlier than our models suggest. If the latter is true, then we need to look further back in time, perhaps even to the earliest moments after the Big Bang. to understand what could have seeded these massive cosmic structures. One possibility is that primordial density fluctuations, small variations in the density of matter in the early universe, may have played a bigger role than previously thought. The cosmic microwave background (CMB), which is essentially the afterglow of the Big Bang, contains tiny temperature variations that represent these density fluctuations. Over billions of years, these fluctuations grew into the cosmic web of galaxies we see today. But what if some of these fluctuations were significantly larger than expected? If certain regions of the early universe had extreme overdensities of matter, they could have formed LQGs before other structures even had a chance to take shape. Another possible explanation involves dark matter and dark energy, two of the most mysterious components of the cosmos. Dark matter is thought to act as the invisible scaffolding that holds galaxies and clusters together, while dark energy drives the accelerating expansion of the universe. If dark matter is not evenly distributed, or if it interacts in ways we do not yet understand, it could have influenced the formation of LQGs. Some scientists propose that early fluctuations in dark matter density could have caused some regions of the universe to collapse into massive structures, forming LQGs at an accelerated rate. Meanwhile, dark energy remains an even bigger mystery. If the force of dark energy has not been uniform throughout cosmic history, then certain regions might have expanded at different rates. This could have allowed some parts of the universe to form huge structures earlier than expected, while others remained relatively empty. If LQGs are linked to variations in dark energy, then they could serve as natural laboratories for studying the nature of this mysterious force. There is also the possibility that LQGs are connected by hidden filaments of matter that we cannot yet detect. The cosmic web, the vast network of galaxies, filaments, and voids, forms due to the large-scale distribution of matter in the universe. If LQGs are aligned along unseen filaments of dark matter, they might not be isolated structures at all, but rather part of a much larger cosmic framework that extends beyond our current observational limits. But what if LQGs are not just natural formations? Some speculative theories suggest that intelligent civilizations, if they exist on an intergalactic scale, could have played a role in their formation. While this idea may seem far-fetched, it is not outside the realm of possibility. If an advanced civilization had the ability to manipulate energy on cosmic scales, could they have influenced the arrangement of quasars or even entire galaxies? Some researchers have suggested that LQGs could be indicators of unknown astrophysical processes, possibly even artificial in nature. If so, then detecting patterns within LQGs, such as unusual alignments or energy signatures, could provide indirect evidence of extraterrestrial intelligence. Even if LQGs are entirely natural, their existence raises profound questions about the ultimate fate of the universe. If such massive structures exist, then their gravitational influence could shape the future evolution of cosmic structures in ways we have yet to predict. Could LQGs eventually merge into even larger formations, creating hyperclusters or supercluster highways? If so, then the universe might not be trending toward uniformity, as current models suggest, but rather toward a future where matter becomes increasingly concentrated into massive, interconnected cosmic megastructures. Future observations will be crucial in solving these mysteries. The upcoming Euclid Space Telescope and the Vera C. Rubin Observatory will provide more detailed maps of the universe's large-scale structure, allowing astronomers to test whether LQGs are isolated anomalies or part of a broader cosmic pattern. If more LQGs are found, we may need to redefine our understanding of cosmic structure formation. If they turn out to be extremely rare, then we must ask, what unique conditions allowed them to form in the first place? Ultimately, the study of LQGs is about more than just understanding quasars or galaxy clusters. It is about challenging our deepest assumptions about the universe. These colossal formations defy expectations, hinting at forces, structures, or processes that we have yet to uncover. They push the limits of our knowledge, forcing us to confront the possibility that there is something fundamentally incomplete about our current theories. The universe is vast, mysterious, and filled with unanswered questions. Large quasar groups are just one of the many cosmic anomalies that remind us how much we have yet to learn. Whether they are relics of the early universe, signs of new physics, or something else entirely, they stand as enigmatic cosmic beacons, challenging us to look deeper, think bigger, and reconsider everything we thought we knew about the nature of space itself. One of the most perplexing aspects of large quasar groups, LQGs, is their relationship with the cosmic web, the vast structure of the universe made up of galaxies, filaments, and voids. According to the lambda cold dark matter model, which is the standard model of cosmology, matter in the universe should be distributed in a way that does not allow structures larger than about 1.2 billion light-years to form. Yet, LQGs defy this prediction. The huge LQG, for example, is over 4 billion light-years across, meaning it not only surpasses theoretical size limits but also challenges our fundamental understanding of how the universe organizes itself. If we think about the cosmic web, it resembles a three-dimensional network where galaxies are connected by long filaments of dark matter and ordinary matter. These filaments form structures known as superclusters, which are among the largest known formations in the universe. However, LQGs seem to take this concept even further. They are not just clusters of galaxies but rather huge chains of quasars, stretching across distances that should be impossible. One explanation for their existence is that LQGs may be aligned along massive dark matter filaments that we have yet to detect. The idea is that these filaments, which act like invisible highways for cosmic structures, may be more extensive and interconnected than we currently understand. If LQGs are simply the brightest visible components of these larger hidden structures, then our current understanding of the universe's large-scale architecture may be vastly incomplete. But how could such massive structures form in the first place? The process of structure formation in cosmology relies heavily on the concept of gravitational collapse. Small fluctuations in the density of matter in the early universe grew over time due to gravity, pulling more matter into dense regions and eventually forming galaxies, clusters, and superclusters. However, for LQGs to exist, these density fluctuations would have to be far more extreme than what our current models allow. This raises the possibility that LQGs formed under unusual or unknown physical conditions. One hypothesis is that during the inflationary period, a brief but powerful expansion of the universe just after the Big Bang, certain regions of space may have expanded differently from others, creating pockets of extreme density variations. These variations could have later given rise to enormous cosmic structures, including LQGs. Another idea is that dark energy, the mysterious force driving the acceleration of the universe's expansion, may not be uniform. If dark energy's strength varies across different regions of space, it could have allowed certain areas to evolve differently, forming structures much larger than expected. This would mean that LQGs are not just unusual clusters of quasars but evidence of a deeper, underlying cosmic force that we have yet to fully understand. Interestingly, LQGs may also hold clues about the early universe's initial conditions. By studying how these structures are distributed and whether they follow any patterns, astronomers hope to uncover hints about how the universe was shaped in its earliest moments. For example, if LQGs tend to be found in certain regions of the sky but not others, it could suggest that the Big Bang itself was not entirely uniform, leading to variations in structure formation that we still see today. Beyond their scientific significance, LQGs also raise profound philosophical questions about our place in the universe. If these structures are real, then they suggest that the cosmos is far more interconnected and organized than we ever imagined. Could it be that the universe follows patterns and principles we have yet to discover? Could LQGs be part of an even larger structure that we are not yet capable of detecting? If so, then the true scale of the universe may be far beyond anything we have considered. As technology advances, future telescopes and observational techniques will allow us to probe even deeper into the cosmos. The Euclid Space Telescope, for example, will map the large-scale structure of the universe with unprecedented precision, potentially revealing new details about LQGs and their role in cosmic evolution. Meanwhile, the Square Kilometre Array, SKA, the world's largest radio telescope, will provide deeper insights into quasars and their connection to large-scale cosmic structures. For now, LQGs remain one of the most perplexing mysteries of space. Whether they are anomalies, relics of an ancient cosmic era, or signs of new physics, they challenge us to rethink our understanding of the universe on the largest scales. As we continue to explore and uncover new cosmic truths, one thing is certain: LQGs are a reminder that the universe is far more complex, structured, and mysterious than we ever imagined. One of the biggest unanswered questions about large quasar groups, LQGs, is whether they represent true physical structures or if their apparent clustering is just an illusion caused by observational bias. In astronomy, we often deal with the challenge of incomplete data. Our telescopes can only detect objects up to a certain distance, and the way we interpret that data is heavily influenced by how we define clusters in the first place. Some researchers argue that what we call LQGs might not be physically connected in the way we think. Instead, they could be random alignments of quasars that just happen to appear as large-scale structures when viewed from Earth. This would mean that the existence of LQGs as actual cosmic megastructures might be a misinterpretation of data rather than a genuine astrophysical phenomenon. However, the counterargument is that the statistical analyses used to identify LQGs are rigorous. The huge LQG, for example, was identified through advanced clustering algorithms, and the likelihood of it forming by chance is incredibly small. If LQGs were just statistical anomalies, we would not expect them to follow consistent spatial distributions across multiple regions of the sky. Yet, astronomers have found several distinct LQGs, suggesting that these structures are not merely artifacts of limited observations. Another major challenge in studying LQGs is that quasars are extremely distant objects, meaning the light we observe from them is often billions of years old. This creates an interesting problem. If we detect an LQG that is, say, 8 billion light-years away, we are seeing it as it was 8 billion years ago. What has happened to that structure in the present day? Is it still a connected megastructure, or have the quasars within it drifted apart due to the universe's expansion? The answer to this question depends on how gravitationally bound these quasar groups are. If LQGs are truly self-contained structures, then they should have remained intact over billions of years. But if they are just temporary alignments, then cosmic expansion and the movement of galaxies over time might have dispersed them, making them look very different today than they did when their light first reached us. One of the most fascinating possibilities is that LQGs could be the precursors to even larger structures that have since evolved into modern superclusters. If this is true, then studying LQGs is like looking back in time at the early stages of cosmic megastructures, offering us a rare glimpse into how the universe's largest formations came to be. But what if LQGs are something else entirely? Some theorists have speculated that these structures might be connected to exotic forms of matter or energy that we do not yet understand. One possibility is that they are linked to dark matter filaments, massive, invisible threads of matter that weave through the universe, connecting galaxies and clusters. If LQGs are tracing the shape of these hidden filaments, they could serve as a map to the unseen scaffolding of the cosmos. Another possibility is that LQGs are influenced by quantum fluctuations from the early universe. According to some models of cosmic inflation, certain regions of space experienced higher energy densities than others, leading to uneven distributions of matter that later formed large-scale structures. If LQGs are remnants of these primordial quantum imprints, they could provide new insights into how the very fabric of space was shaped in the moments following the Big Bang. One of the strangest ideas related to LQGs is the possibility that they could be connected to alternate dimensions or cosmic anomalies. Some physicists have proposed that the universe may contain extra spatial dimensions beyond the three we experience. If these hidden dimensions influence the distribution of matter in unexpected ways, they could create gigantic structures that do not fit within our current understanding of physics. While this might sound like science fiction, there is already precedent for considering such ideas. The concept of brane cosmology, which arises from string theory, suggests that our universe could be a three-dimensional membrane, floating in a higher dimensional space. If true, then the formation of LQGs could be influenced by forces beyond our observable universe, forces that act across dimensions we cannot directly perceive. Even without invoking extra dimensions, LQGs could challenge some of the fundamental assumptions we make about the universe's large-scale structure. If they are real, Then the cosmological principle, the idea that the universe is uniform on large scales, may need to be revised. LQGs suggest that large-scale irregularities exist, meaning that the universe may have far more structure and complexity than previously thought. Future discoveries will help clarify these mysteries. The next generation of telescopes, including the James Webb Space Telescope, JWST, and the Vera C. Rubin Observatory, will provide even more detailed observations of distant quasars, potentially revealing new LQGs or refining our understanding of their distribution. Meanwhile, deep sky surveys will allow astronomers to map the cosmic web with higher precision, helping to determine whether LQGs are truly distinct structures or simply extreme outliers in an otherwise uniform universe. Regardless of what the future holds, LQGs remain one of the most intriguing cosmic phenomena ever discovered. They challenge everything we thought we knew about the limits of cosmic structure, raise profound questions about the early universe, and hint at possibilities that extend far beyond our current theories. Whether they turn out to be mere statistical anomalies or evidence of new physics, one thing is certain: the universe still holds secrets far greater than we can imagine. The deeper we investigate large quasar groups, LQGs, the more we realize how much they challenge our fundamental understanding of cosmic structure. If LQGs truly exist as stable formations spanning billions of light years, they push against the limits of what we thought was possible in the universe. Our current models, particularly the cosmological principle, suggest that on large enough scales, the universe should appear homogeneous and isotropic, meaning it should look roughly the same in every direction, without major irregularities. But the existence of LQGs seems to contradict that idea. Astronomers have long believed that while galaxies and clusters may form intricate structures, they should not exceed a certain size limit, known as the homogeneity scale, which is estimated to be around 1.2 billion light-years. This means that, beyond this distance, the distribution of matter in the universe should smooth out and become uniform. Yet LQGs like the huge LQG, spanning a staggering 4 billion light-years, seem to defy that boundary. If such structures are real, they challenge our understanding of how matter is arranged on the largest cosmic scales. This raises several questions. Are LQGs just statistical flukes, or are they genuine physical structures? If they are real, how did they form? Current models of cosmic evolution, based on dark matter and dark energy, struggle to explain the existence of such enormous configurations. The gravitational interactions required to maintain a structure of this size should, in theory, take longer than the age of the universe itself. So how did these quasar groups assemble so early in cosmic history? One possible explanation involves the role of dark matter. According to the lambda cold dark matter model, most of the universe's mass is made up of invisible dark matter, which interacts only through gravity. This dark matter forms a vast web-like structure known as the cosmic web, within which galaxies and quasars are thought to be arranged. It is possible that LQGs are simply dense regions within this cosmic web, where the gravitational pull of dark matter has drawn quasars together into large-scale patterns. However, this still does not fully explain how LQGs have remained gravitationally bound over billions of years. If these structures are real, they must have some underlying connection that keeps them together despite the ongoing expansion of the universe. This has led some astronomers to speculate that LQGs may be linked by filaments of dark energy, or exotic forces that we do not yet understand. Another possibility is that LQGs formed due to early quantum fluctuations in the fabric of spacetime itself. During the first moments after the Big Bang, the universe experienced rapid expansion in a process known as cosmic inflation. If certain regions of space contained slightly more energy than others, they could have seeded the formation of large-scale structures. If LQGs are remnants of these early fluctuations, they could provide valuable clues about the physics of the early universe and the nature of cosmic inflation. But what if LQGs are not entirely natural phenomena? Some researchers have considered more speculative ideas, including the possibility that LQGs could be evidence of advanced cosmic engineering. If an advanced extraterrestrial civilization had the ability to manipulate cosmic structures on a grand scale, could they have influenced the formation of LQGs? While this idea is purely hypothetical, it raises an interesting question. Could the distribution of quasars in the universe be shaped, at least in part, by intelligent design rather than just natural gravitational processes? Although this idea might seem far-fetched, some physicists have proposed that extremely advanced civilizations, perhaps billions of years older than humanity, might possess the capability to manipulate black holes, galaxies, or even the structure of space-time itself. If this were the case, then LQGs might not just be random clusters of quasars, but instead artificial megastructures created for unknown purposes. Of course, there is no direct evidence for this idea, but the very fact that LQGs exist at all forces us to reconsider the fundamental nature of cosmic structure. Could they be linked to processes that go beyond our current understanding of physics? Are they connected to hidden dimensions, exotic matter, or other unknown forces that shape the universe on scales we cannot yet comprehend? The search for answers continues. Upcoming missions, such as the Euclid Space Telescope and the Nancy Grace Roman Space Telescope, will provide new insights into the large-scale structure of the universe, potentially revealing new LQGs or offering clues about their nature. Meanwhile, advances in computational modeling will allow scientists to simulate the evolution of these structures in greater detail, helping to determine whether they are genuine cosmic features or just statistical anomalies. One thing is certain: large quasar groups remain one of the greatest space mysteries of our time. Whether they represent the largest cosmic structures ever discovered, evidence of unknown physics, or simply a puzzle we have yet to fully solve, their existence challenges our understanding of the universe. And as new discoveries continue to reshape our view of the cosmos, the true nature of LQGs may turn out to be even stranger than we ever imagined. The mystery of large quasar groups, LQGs, extends beyond their sheer size. Their existence forces us to rethink the fundamental rules that govern the cosmos. If the universe is supposed to be uniform on a large enough scale, how do these massive structures fit into that picture? The possibility that they are statistical anomalies is always on the table, but if they are truly gravitationally bound entities, it suggests that the early universe contained far more structure and organization than our models predict. One possible explanation is that we are misunderstanding the formation and evolution of quasars themselves. Quasars are powered by supermassive black holes at the centers of galaxies, and their extreme luminosity comes from the violent process of material falling into these black holes. The question is, why do quasars appear to be clustering into these massive formations? If LQGs were merely chance alignments, we would expect their distribution to follow a more random pattern, but instead, we find that they appear linked across billions of light years. Could there be a deeper connection between quasars and the large-scale structure of the universe? Some astronomers speculate that quasars might form preferentially along cosmic filaments, the vast tendrils of matter that make up the cosmic web. This would mean that LQGs are not standalone entities but rather regions of enhanced quasar activity within this web-like structure. However, this still does not fully explain why they appear to be gravitationally bound despite their immense distances. One theory suggests that LQGs could be relics from an earlier phase of cosmic history, where matter was more densely packed. If these structures formed when the universe was younger and galaxies were closer together, it is possible that they retained their structure even as the universe expanded. However, this would imply that LQGs somehow resisted the effects of cosmic expansion, which should have stretched them apart over billions of years. Could this mean that LQGs are connected by forces beyond gravity, perhaps exotic forms of dark matter or dark energy? Some physicists have proposed that LQGs could be linked through primordial magnetic fields, remnants from the early universe that could have influenced the distribution of matter on a vast scale. If magnetic fields played a role in shaping the early universe, they might have helped guide the formation of massive structures like LQGs. However, this idea remains speculative, as we still do not fully understand the role of cosmic magnetism in large-scale structure formation. Another perplexing aspect of LQGs is their apparent alignment with certain cosmic patterns. Some studies have suggested that quasars within LQGs are not just randomly distributed but may exhibit coherent spin alignments, meaning their rotation axes tend to point in the same direction. If this is true, it could indicate the presence of unknown forces acting across vast cosmic distances. Could this be evidence of hidden physics at play? This ties into another major cosmic puzzle, the possibility that LQGs are connected to the large-scale anisotropies of the universe. Certain observations, such as the axis of evil anomaly in the cosmic microwave background (CMB), suggest that the universe may have hidden patterns or preferred directions that we do not yet understand. If LQGs are somehow aligned with these cosmic patterns, it could mean that our current models of the universe are incomplete. Some researchers have even speculated that LQGs could be evidence of previous cosmic cycles. The conformal cyclic cosmology (CCC) hypothesis, proposed by Sir Roger Penrose, suggests that the universe undergoes endless cycles of expansion and rebirth. If this is true, structures like LQGs might be leftover imprints from a previous universe, providing a direct link between past and present cosmic epochs. But what if LQGs are not natural formations at all? While there is no direct evidence to support this, some have entertained the possibility that LQGs could be artificially engineered. If an advanced civilization had the technology to manipulate galaxies or control the behavior of black holes, could they have shaped LQGs for a purpose we do not yet understand? This concept, while speculative, raises fascinating questions about the potential influence of intelligence on cosmic scales. The true nature of large quasar groups remains one of the most profound space mysteries. Whether they are genuine physical structures, statistical anomalies, or evidence of hidden forces, their existence challenges our understanding of the universe in ways we are only beginning to explore. As new telescopes and observational techniques allow us to probe deeper into the cosmos, we may finally uncover the answers to this grand cosmic puzzle. But until then, LQGs remain one of the most intriguing and unexplained phenomena in astrophysics. If large quasar groups, LQGs, are real, physically bound structures, then they directly challenge one of the most fundamental principles in cosmology, the cosmological principle. This principle states that, on sufficiently large scales, the universe should look the same in every direction, with no preferred spots of extreme clustering. Yet LQGs defy this assumption by forming massive, structured regions that stretch across billions of light-years. This raises an important question: is the universe truly homogeneous on the largest scales, or is there hidden order that we have yet to fully understand? One possibility is that our understanding of cosmic evolution is incomplete. If LQGs are remnants from an earlier phase of the universe, then they could represent a missing link in our models of galaxy formation. Most of our current understanding of structure formation relies on the idea that galaxies and clusters grew out of small density fluctuations in the early universe, which were later amplified by gravity and dark matter interactions. However, the existence of LQGs suggests that some regions of the cosmos experienced a much more extreme form of structure growth. Could this mean that the early universe was not as uniform as we thought? Some scientists propose that LQGs may have formed in regions where dark matter was unusually dense, leading to the rapid clustering of quasars and galaxies. If so, this would imply that dark matter is not evenly distributed but instead clumps together in massive, unexpected ways. This could provide crucial insights into the nature of dark matter itself. Perhaps it interacts with normal matter in ways we do not yet fully understand. Another possibility is that the large-scale structure of the universe is influenced by unknown forces. For instance, some theoretical models suggest that the universe may have extra dimensions beyond the three we observe. If true, LQGs could be the visible imprints of higher-dimensional structures interacting with our own universe. This concept ties into ideas from string theory, which suggests that hidden dimensions could shape the way matter and energy distribute themselves across cosmic scales. Some researchers have even speculated that LQGs could be the result of ancient cosmic filaments that formed before the universe fully expanded. These filaments, which are thought to be the largest structures in the universe, could have acted as gravitational highways, funneling quasars into these massive, elongated formations. If this is the case, then LQGs might not be clusters at all, but rather long chains of quasars strung together by the invisible threads of the cosmic web. Yet, despite these theories, one of the biggest mysteries surrounding LQGs is why quasars within them appear to be aligned. Some observations suggest that quasars within the same LQG tend to have similar rotation axes, as if they were somehow synchronized across vast cosmic distances. This is highly unusual, as there should be no known force capable of linking these objects in such a coordinated manner. Could this alignment be evidence of a deeper, underlying order in the universe? Some astronomers believe that this could be a sign of a cosmic magnetic field that existed in the early universe, guiding the orientation of quasars on a scale never before imagined. Others have suggested that this could be the fingerprint of a fundamental physical law that we have yet to discover, one that dictates how matter behaves on the largest cosmic scales. But what if LQGs are not just natural formations? Could they be signs of intelligent design? While this idea is purely speculative, some theorists have pondered whether an advanced civilization could have manipulated the formation of quasars, perhaps for unknown cosmic engineering purposes. If we consider the possibility that intelligent life could exist on scales beyond what we currently imagine, then LQGs could be a form of megastructure, one that spans billions of light years and serves a function we cannot yet comprehend. While there is no evidence to support this hypothesis, it is a fascinating thought experiment. If an advanced civilization had access to energy on a cosmic scale, they might have the ability to shape the evolution of galaxies and quasars. Could LQGs be some kind of massive intergalactic energy grid? Or perhaps they are beacons, sending signals across the universe in ways we have yet to detect? The implications of LQGs stretch beyond astrophysics. They force us to reconsider the fundamental structure of reality itself. Are they relics from a past cosmic cycle? Are they clues to a hidden force shaping the universe? Or are they simply statistical anomalies that just happen to look like structures? As technology advances and new telescopes allow us to peer deeper into the cosmos, we may finally uncover the answers to these questions. Future surveys, such as those conducted by the James Webb Space Telescope and upcoming next-generation observatories, may provide critical insights into the nature of LQGs and their place in the cosmic puzzle. But for now, they remain one of the greatest mysteries of space, challenging everything we think we know about the universe. Their existence hints at a cosmos far more complex than we ever imagined, filled with structures, forces, and perhaps even intelligence beyond our current understanding. If large quasar groups are real, physically bound structures, they could mean that the universe has hidden patterns of organization that we haven't fully grasped yet. It raises the question, what if the structure of the cosmos is not random but follows a deeper, more complex order? If LQGs exist on such a massive scale, does that mean even larger structures could be waiting to be discovered? Could there be megaclusters of galaxies or even larger formations that completely rewrite our understanding of how the universe is arranged? One of the most controversial aspects of LQGs is that they appear to challenge the idea that the universe has a cosmological limit to how large structures can be. The Sloan Great Wall, a giant wall-like arrangement of galaxies, is another example of a cosmic structure that pushes the boundaries of what should be possible. But LQGs go even further. If they are real, they could mean that the universe has structures that break the known rules of physics. One major question that remains is how LQGs formed in the first place. Standard models of cosmic evolution suggest that galaxies and quasars form in small clusters and gradually merge into larger structures over billions of years. But LQGs seem to be too large and too organized to have formed through the slow merging process we currently understand. This suggests that either they formed extremely quickly in the early universe, or there is a missing factor in our understanding of how the universe evolved. Some researchers have proposed that LQGs could have been created by a process we have yet to discover, such as primordial cosmic turbulence. If the early universe contained violent waves of energy that shaped the distribution of matter, then these waves might have imprinted massive patterns onto the cosmos, forming structures like LQGs. Another possibility is that dark matter played a much larger role than we currently assume, creating gravitational wells that pulled quasars into these massive arrangements. Another mind-bending idea is that LQGs could be signs of an earlier universe overlapping with our own. Some models of physics suggest that the Big Bang was not the beginning of everything, but just the latest cycle in a much older, repeating universe. If this is true, then LQGs might be fossils of an earlier cosmic cycle, structures that somehow survived the transition from one version of the universe to the next. This idea ties into another strange phenomenon, the mysterious alignment of quasars within LQGs. In theory, quasars should have random orientations, with their jets pointing in all directions. But in some LQGs, quasars appear to be aligned, as if they were affected by a common force or pattern. This could be a clue that there is a hidden order in the universe that we have yet to understand. One possible explanation for this alignment is that a cosmic magnetic field existed in the early universe, influencing the orientation of quasars on a scale far beyond anything we've seen before. If this is true, it could mean that the universe has an underlying structure shaped by invisible forces, a kind of cosmic blueprint that dictates how matter arranges itself over billions of years. Another possibility is that LQGs are part of a much larger structure that we haven't fully mapped yet. If we could step back far enough and see the universe from an even bigger perspective, we might discover that LQGs are just small pieces of an even greater pattern, one that stretches across the entire cosmos. But perhaps the most unsettling possibility is that our understanding of space itself is flawed. What if the way we measure distance and scale in the universe is missing something fundamental? Could it be that LQGs only appear to be huge, but in reality, space bends or warps in ways we don't yet understand? Some theories suggest that the fabric of SpaceTime might be curved in unexpected ways, creating illusions of massive structures where none exist. If this is the case, then LQGs might not be real physical objects at all, but rather artifacts of the way our universe distorts light and gravity. Regardless of the explanation, one thing is clear: LQGs are one of the biggest cosmic mysteries ever discovered. They defy expectations, break the rules, and force us to question everything we thought we knew about the universe. If we can unlock their secrets, we may gain insight into the fundamental nature of reality itself. And perhaps, just perhaps, LQGs are only the beginning. If we continue to explore, what else might we find out there? Could there be even larger, even stranger structures waiting to be discovered? Ones that completely reshape our understanding of space, time, and existence? If large quasar groups are just a piece of an even greater cosmic puzzle, then what else could be out there? Could there be even larger structures, perhaps spanning billions of light years, forming patterns beyond human comprehension? The idea of hidden cosmic order is a tantalizing one. It suggests that the universe may not be as random as we once believed, that there might be a deeper structure guiding the formation of galaxies, quasars, and even entire superclusters. One possibility is that these enormous structures could be evidence of unknown cosmic forces at work. The universe is governed by four fundamental forces: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. But what if there is a fifth force, one that operates on an unimaginable scale, influencing the alignment and distribution of matter across the cosmos? If such a force exists, it might be the key to explaining the impossible scale of LQGs. Perhaps, instead of forming through standard gravitational attraction alone, these structures were shaped by an unseen cosmic field, one that dictated their massive, interconnected patterns. Some physicists have speculated that dark energy, the mysterious force driving the acceleration of the universe's expansion, could play a role in structuring the cosmos on these massive scales. But so far, no definitive connection has been found. There is another, even more radical possibility. LQGs could be evidence that the universe is much older than we think. The standard model of cosmology tells us that the universe is about 13.8 billion years old, but what if it's far older? What if LQGs are ancient remnants of a previous universe, structures that survived a cosmic cycle of destruction and rebirth? Some models of physics suggest that the Big Bang was not the absolute beginning, but rather a transitional event between different phases of the universe. If this is true, then LQGs might be leftovers from an earlier epoch, a time when the rules of physics were different and allowed for the formation of these gigantic structures. If this idea is correct, then studying LQGs could give us direct evidence of what came before our universe, offering the first glimpse into the cosmic history that existed before the Big Bang. Another mind-bending concept is that LQGs could be illusions, not in the sense that they aren't real, but rather that their immense size might be a result of how we perceive space itself. What if our current models of distance, expansion, and cosmic structure are missing something fundamental? There is a theory that suggests the universe might be shaped like a giant, curved structure, meaning that objects that appear extremely far apart might actually be much closer than we think. If this is true, then LQGs might not be physically enormous clusters of quasars, but rather the result of the way light and gravity interact across vast cosmic distances. This could mean that the universe contains hidden dimensions, beyond the 3 dimensions of space and the one of time that we experience. Some physicists believe that the cosmos could have extra spatial dimensions, curled up at scales too small for us to detect. If these extra dimensions somehow affect the way light travels through space, they could create the illusion of massive structures, making objects appear far larger and more connected than they truly are. One of the strangest ideas surrounding LQGs is the possibility that they could be linked to something beyond our universe entirely. Some speculative theories suggest that LQGs might be the cosmic fingerprints of other universes interacting with our own. Imagine that our universe is just one of many, floating in a higher dimensional space, like bubbles in a vast cosmic ocean. If these bubbles occasionally collide or interact, they might leave massive imprints in the form of large-scale structures like LQGs. This idea is connected to the concept of the multiverse, the idea that there may be countless universes beyond our own, each with its own unique set of physical laws. If LQGs are indeed remnants of such interactions, then they could be the first observable evidence that the multiverse is real. But perhaps the most unsettling idea is that LQGs are evidence that our universe is not what we think it is. What if reality itself is a kind of simulation, and LQGs are artifacts of the way this simulation is structured? This might sound like science fiction, but some physicists take the idea of a simulated universe seriously. If we are living inside a vast computational framework, then LQGs could be glitches in the cosmic code, evidence that our reality is governed by underlying rules that are not fully natural. If this were true, then discovering the full nature of LQGs might allow us to uncover the deepest secrets of existence itself. Who or what created the simulation, why it exists, and what lies beyond its boundaries. Regardless of what they truly are, LQGs stand as one of the greatest mysteries of modern cosmology. They challenge the limits of our understanding, pushing us to reconsider the nature of space, time, and reality itself. And if history has taught us anything, it's that every time we think we've reached the edge of knowledge, the universe reveals something even stranger waiting just beyond. So the next time you look up at the night sky, remember, somewhere out there, beyond the stars we can see, the universe might be hiding structures so vast and so mysterious that they could rewrite everything we think we know about existence. The deeper we dive into the mystery of large quasar groups, the more questions arise. Are these structures merely statistical anomalies? Or do they hold the key to a deeper, more fundamental truth about the cosmos? If LQGs truly exist at the scales observed, they pose a direct challenge to the cosmological principle, the foundational idea that, on large scales, the universe should be homogeneous and isotropic. This principle has been the backbone of modern cosmology for decades, asserting that no region of the universe should be drastically different from another when viewed on a cosmic scale. But LQGs defy this assumption. They show that, in some areas of space, matter clumps together in staggering formations, while in others, vast voids stretch across unimaginable distances. If this principle is wrong, or at least incomplete, it could mean that the very fabric of space is not as uniform as we once believed. This opens up possibilities that range from new laws of physics to the idea that the universe itself has a hidden architecture, one that shapes the way galaxies, quasars, and even cosmic structures form. One explanation for the existence of LQGs involves primordial fluctuations, small density variations in the early universe that eventually grew into the large-scale structures we see today. The standard model of cosmology explains that these fluctuations, caused by quantum effects in the early moments of the Big Bang, were stretched by cosmic inflation into the massive cosmic web of galaxies and voids we observe today. But could these fluctuations have been more extreme than we thought? If certain regions of space had vastly higher densities than others, it could explain why some areas formed enormous superstructures while others became vast cosmic deserts. This brings us to another mind-boggling question. Could LQGs be remnants of an earlier cosmic event, something that predates even the cosmic microwave background radiation? Some scientists speculate that these massive structures could be fossils from before the observable universe, remnants of a pre-Big Bang reality. This idea is rooted in the concept of cyclic universes, where the cosmos undergoes endless cycles of expansion and contraction. If the universe existed in a previous form before our current expansion, perhaps these structures are leftovers from that era, surviving through an unknown cosmic transition. There's also a possibility that LQGs hint at the influence of dark matter and dark energy in ways we haven't yet understood. We already know that dark matter makes up around 85% of all matter in the universe, yet we have no direct way of seeing or detecting it except through its gravitational effects. If LQGs formed in areas with an unusually high concentration of dark matter, this could explain why quasars in these regions gravitationally cluster together in such unexpected ways. Some researchers have even proposed that there might be entire hidden structures of dark matter, invisible to us but shaping the visible cosmos in ways we haven't yet realized. And then, there's the concept of cosmic filaments, giant threads of galaxies and dark matter stretching across space, connecting vast clusters like a vast, interwoven web. Could LQGs be part of an even larger, unseen structure, a supercluster, spanning even greater distances than we can currently measure? This idea aligns with recent discoveries of even larger cosmic structures, such as the Giant Arc, a massive arrangement of galaxies stretching 3.3 billion light-years across. If such enormous formations exist, it suggests that our current understanding of how matter organizes itself in the universe is deeply incomplete. But perhaps the strangest possibility is that LQGs aren't natural at all. Could they be the result of some unknown, non-random process? If the universe has hidden rules or organizing principles, LQGs might be the first sign of a deeper cosmic order that we have yet to uncover. One possibility is that they were shaped by ancient cosmic forces, operating on timescales and scales we can barely imagine. Another, even more speculative idea, is that LQGs are artificial in some way, the result of intelligence far beyond our own, shaping the structure of the cosmos itself. Could an advanced civilization, billions of years older than us, have manipulated the universe on a grand scale? Some theorists have suggested that, if a civilization reached a Type 3 or even Type 4 status on the Kardashev scale, it might be capable of engineering entire galaxies, creating star structures on a level we cannot yet comprehend. Of course, this idea is purely speculative. But the fact remains, LQGs should not exist, and yet they do. Their presence forces us to rethink some of the most fundamental ideas in cosmology, from the nature of large-scale structure formation to the possibility that the universe itself is more structured, complex, and interconnected than we ever imagined. As we continue to map the cosmos with more powerful telescopes and techniques, we may find that LQGs are just the beginning of a larger pattern, one that will eventually force us to rewrite the laws of physics as we know them. So what do these immense structures truly mean? Are they statistical oddities, unexplained but ultimately insignificant? Or are they the first cracks in our understanding of the universe, hints that the cosmos is far more intricate than we ever dared to believe? One thing is certain, large quasar groups are among the greatest space mysteries of our time. And as we continue to study them, we may find that they hold the key to secrets about the universe that we have yet to even imagine. The implications of large quasar groups stretch far beyond their sheer size. If these colossal structures truly exist as we observe them, then the fabric of the universe may be far more complex than our models suggest. The idea that the universe is structured in a homogeneous and isotropic manner has been a cornerstone of cosmology. It underpins the lambda cold dark matter model, the most widely accepted framework for understanding the universe's formation and evolution. However, the discovery of LQGs challenges this principle at a fundamental level. When astronomers first began studying the huge Large Quasar Group, huge LQG, one of the largest LQGs ever found, stretching over 4 billion light-years across, they faced a problem. According to current cosmological theories, no structure should be this large. In fact, the theoretical limit for cosmic structures, based on the lambda cold dark matter model, is around 1.2 billion light-years. Anything significantly larger than this violates our understanding of how matter organizes itself over vast distances. This raises a crucial question: how did these large quasar groups form, and why do they exist at all? One hypothesis suggests that LQGs formed due to density fluctuations in the early universe. These fluctuations were tiny variations in the density of matter and energy that emerged shortly after the Big Bang. Over time, gravity amplified these fluctuations, leading to the formation of galaxies, galaxy clusters, and ultimately, superclusters. But the problem with this explanation is that LQGs are too large to have emerged from known density fluctuations alone. Some researchers believe that LQGs could be the result of cosmic filaments, massive strands of galaxies and dark matter that form the scaffolding of the cosmic web. If multiple filaments became unusually dense in specific regions, they might have triggered the formation of an LQG, causing quasars to cluster together in a way that defies conventional models. But what if these structures are not just anomalies but signs of a deeper, hidden order within the universe? If LQGs truly defy standard physics, then they could indicate that the distribution of matter in the cosmos follows patterns we have yet to understand. Could there be an unknown force, an unseen influence that dictates the way galaxies, quasars, and cosmic structures form on the largest scales? One radical theory suggests that LQGs might be relics of a previous universe. The idea of a cyclic cosmos, where the universe undergoes endless cycles of expansion and contraction, has been explored in various cosmological models. If our universe had a predecessor, and if remnants of its structure somehow survived the transition to our current era, then LQGs might be ancient imprints from an earlier cosmic epoch. This concept aligns with the theory of conformal cyclic cosmology, proposed by physicist Roger Penrose. According to this model, the universe undergoes infinite cycles, where each new universe is born from the remnants of the one before it. If this is true, then LQGs might be leftover structures from a previous cycle, carrying with them the fingerprints of a reality far older than we ever imagined. Another possibility is that LQGs are influenced by dark matter and dark energy in ways we don't yet understand. We know that dark matter makes up the majority of the universe's mass, yet it remains completely invisible, only detectable through its gravitational effects. If LQGs are located in regions with exceptionally high concentrations of dark matter, this could explain why quasars in these areas became gravitationally bound together, forming these immense superstructures. Similarly, dark energy, the mysterious force driving the accelerated expansion of the universe, might also play a role. If dark energy behaves differently in certain parts of the cosmos, it could affect the way matter clusters, leading to localized regions where massive structures like LQGs could emerge. But perhaps the most unsettling possibility is that LQGs are not natural formations at all. Could they be the product of cosmic engineering on an unfathomable scale? The idea that advanced civilizations could manipulate entire galaxies or alter the large-scale structure of the universe sounds like science fiction, but some theorists argue that it's not entirely out of the question. According to the Kardashev scale, civilizations can be classified based on their ability to harness energy. A Type 3 civilization would have the ability to control energy at the scale of an entire galaxy, while a Type 4 civilization could manipulate energy at the level of the universe itself. If such a civilization existed, it might be capable of reshaping cosmic structures, clustering quasars together for unknown purposes. Could LQGs be evidence of such a civilization's handiwork? If so, what would be their goal? Were these structures created as beacons, signaling their presence to others across the cosmos? Or were they constructed for purposes beyond our comprehension, perhaps to manipulate the fundamental fabric of space-time itself? Even if the idea of an artificial origin seems far-fetched, the very existence of LQGs demands that we rethink the way the universe operates. Their presence suggests that cosmic structures can be larger, more complex, and more organized than our current models predict. And if LQGs are just the beginning, what else might be out there, lurking in the depths of the universe, waiting to be discovered? As telescopes become more advanced and our observational techniques improve, we will continue to map the universe in greater detail. If we find more LQGs, or even larger structures beyond them, it may force us to confront a reality where the universe is far more structured than we ever imagined. For now, the mystery of large quasar groups remains unsolved. But with each new discovery, we inch closer to uncovering the truth about these colossal formations. Are they cosmic anomalies, ancient relics, or evidence of a deeper order in the universe? One thing is certain: the more we learn about LQGs, the more we realize just how little we truly understand about the universe. The deeper we dive into the enigma of large quasar groups, the more questions arise about the true nature of the universe. If LQGs are not supposed to exist within our current cosmological models, then either our understanding is flawed, or we are missing a crucial piece of the puzzle, something fundamental about how the universe arranges itself on a massive scale. Could it be that our cosmic map is only scratching the surface of an even more intricate reality? One of the most perplexing aspects of LQGs is their sheer gravitational coherence. Given their immense scale, the quasars within these groups should not be able to remain gravitationally bound, yet they appear to do so. This raises an interesting question. Is there an unseen force keeping these structures together? One possibility is that the influence of dark matter is far greater in these regions than previously thought. If LQGs exist in areas where dark matter is particularly dense, it could provide the additional gravitational pull necessary to keep quasars clustered together over billions of years. But this theory also comes with complications. The distribution of dark matter in the universe is not entirely understood, and while it is thought to follow the cosmic web's large-scale structure, there is no definitive evidence that it would naturally form structures as immense as LQGs. Another possible explanation is that LQGs are not physically connected in the way we think. What if, instead of being massive structures held together by gravity, they are instead optical illusions caused by an unusual alignment of quasars in the sky? If quasars are positioned along the same line of sight due to cosmic expansion or distortions in spacetime, it could make them appear as part of a larger structure when, in reality, they are much farther apart than they seem. This idea brings us to an even deeper mystery: the nature of spacetime itself. Could LQGs be the result of cosmic warping effects that make certain regions of space appear more clustered than they actually are? If so, then we may need to rethink our assumptions about how we measure distances on cosmic scales. One radical hypothesis suggests that LQGs may be a manifestation of cosmic strings, hypothetical one-dimensional defects in spacetime that could have formed in the early universe. If these strings exist, they could serve as attractors for matter, causing quasars and galaxies to cluster along them in a way that produces structures like LQGs. While no direct evidence for cosmic strings has been found, some physicists believe they could be responsible for strange gravitational effects observed in the universe. But what if LQGs are even stranger than we think? What if they represent a breakdown in the fundamental laws of physics? The cosmological principle, which states that the universe is homogeneous and isotropic on large scales, is one of the cornerstones of modern astrophysics. It is the assumption that underpins all of our major theories about how the universe formed and evolved. If LQGs truly violate this principle, then our entire understanding of cosmology may need to be rewritten. Could LQGs be evidence that the universe is not as uniform as we once believed? Could they be the first signs that the large-scale structure of the cosmos is far more chaotic and uneven than we ever imagined? If this is the case, then it may mean that galaxies and other cosmic objects are arranged in a way that defies our current models, pointing toward a hidden order in the fabric of reality. This idea connects to another controversial possibility, that LQGs are the result of an ancient cosmic event that shaped the structure of the universe itself. Some astronomers have speculated that early in the universe's history, there may have been powerful shockwaves or energy bursts that created irregularities in the distribution of matter, leading to the formation of structures like LQGs. If this is true, then it suggests that LQGs may be relics of a much older cosmic phenomenon, one that left an imprint on the universe in ways we are only beginning to understand. Even more intriguing is the possibility that LQGs could be connected to the nature of time itself. If time behaves differently on the largest scales, could it be that LQGs are evidence of a deeper, hidden structure in spacetime? Some physicists have proposed that time may not flow uniformly across the universe, and that certain regions may experience different rates of expansion or contraction. If LQGs exist in areas where time behaves differently, it could explain why they appear to be gravitationally bound despite their immense size. This brings us back to the idea that LQGs may not be natural formations at all. Could they be intentional structures, created by an advanced intelligence with the ability to manipulate cosmic-scale matter? If a civilization had access to exotic physics beyond our understanding, it might be capable of arranging quasars in a specific way to serve a purpose we cannot yet comprehend. One mind-bending possibility is that LQGs are actually vast cosmic computers, designed to perform calculations on a scale beyond anything we can imagine. If a civilization reached a level of technological advancement where it could manipulate entire galaxies, it might use quasars as computational nodes, processing information in ways that are completely alien to us. Could we be looking at evidence of an ancient intelligence encoded into the very structure of the universe? Or, even more disturbingly, could LQGs be signals left behind by a civilization that no longer exists? If an advanced species once dominated the cosmos but has since vanished, then LQGs might be their lasting imprint, a cosmic signature that continues to persist billions of years after they are gone. Whether LQGs are natural formations, remnants of an earlier universe, or something far stranger, one thing is certain: they are rewriting what we thought we knew about the cosmos. The more we study them, the more they challenge our assumptions, forcing us to consider possibilities that once seemed impossible. As technology advances and future telescopes allow us to peer even deeper into the universe, we may finally unlock the secrets of these massive structures. Will we discover more LQGs stretching across the cosmos in ways that defy explanation? Or will we find something even bigger, something so vast, so incomprehensible, that it forces us to rethink everything we know? The answer lies out there, hidden among the quasars, waiting to be uncovered. But until we solve the mystery, large quasar groups remain one of the most perplexing, mind-bending enigmas in the universe. Large quasar groups, LQGs, are more than just cosmic oddities. They are deep cracks in the foundation of our understanding of the universe. If they truly exist in the way we currently observe them, then something fundamental about our cosmological models is either incomplete or outright wrong. The more we analyze these structures, the more unsettling questions arise. What if LQGs are evidence of an undiscovered force? What if they hint at a larger, unseen structure to the universe? Or, even more dramatically, what if they are proof that the universe itself is shaped by forces far beyond what we can currently comprehend? One of the most pressing problems with LQGs is the sheer contradiction they pose to the cosmological principle, the idea that the universe, when viewed on a large enough scale, should look roughly the same in every direction. This principle is the basis for all our major theories about how the universe formed and evolved. It assumes that matter is distributed evenly when we zoom out far enough. But LQGs defy this assumption in the most dramatic way possible. They are so large that they break the expected uniformity of the cosmos. If the universe were truly homogeneous on the largest scales, LQGs should not exist at all. This leads to a disturbing possibility. What if the universe is far more structured than we ever imagined? What if, rather than being a random scattering of galaxies and quasars, the cosmos is arranged in a pattern we have yet to decode? Some physicists have even speculated that LQGs could be part of a larger cosmic web, a hidden framework that extends beyond our ability to observe. Could these immense structures be connected to an unseen force, one that subtly shapes the distribution of matter across the entire universe? One potential explanation is that LQGs are tied to the very early universe, when matter was first forming into the large-scale structures we see today. If some regions of the universe experienced different rates of expansion due to subtle variations in dark matter or dark energy, it could have led to irregularities in the cosmic web, creating massive clusters like LQGs. This would mean that these structures are fossilized remnants of an ancient cosmic era, frozen in time as echoes of the universe's chaotic birth. But what if LQGs are not just leftovers from the past, but active players in shaping the cosmos? Some researchers have proposed that LQGs could be influencing their surroundings in ways we do not yet understand. Could the immense energy output of these quasars be altering space-time itself? If so, then LQGs might not just be passive structures, they could be part of a vast, interwoven network of energy, affecting the gravitational balance of the universe on a scale beyond anything we have considered before. This concept leads us into even more speculative territory. What if LQGs are not natural formations at all? Could they be evidence of an advanced intelligence operating on a cosmic scale? If a civilization reached a level of technological advancement beyond anything we can comprehend, it might be capable of manipulating entire galaxies, shaping quasars to serve as energy sources or even communication beacons. If LQGs are artificially constructed, then their existence would be the most profound discovery in human history, proof that intelligence exists on a scale beyond anything we have ever imagined. One possibility is that LQGs could serve as intergalactic power stations, harnessing the immense energy of quasars for some unknown purpose. If an advanced civilization needed energy on an unimaginable scale, they might arrange quasars into massive structures, using them as cosmic batteries to fuel their technology. But if this is true, then who, or what, created them? And why? Another possibility is that LQGs are messages, not machines. Some physicists have speculated that highly advanced civilizations might communicate using entire galaxies, encoding information into the way matter is arranged on the largest scales. If this is the case, then LQGs could be part of a cosmic message, one that we have only just begun to decipher. But what if LQGs are not signs of intelligence, but something even stranger? What if they are evidence of a deeper structure to reality itself? Some physicists have suggested that the universe may be far more complex and layered than we currently believe. Could LQGs be a sign that our understanding of space-time is incomplete? Could they be the visible imprint of a hidden dimension, one that stretches beyond the boundaries of our perception? If this is true, then LQGs might be the key to unlocking a new understanding of the universe. They could reveal that the cosmos is not simply an expanding void, but something far richer and more intricate than we ever imagined. They might even provide clues to one of the greatest mysteries of all, the true nature of reality itself. As technology advances, we will continue to probe deeper into these cosmic structures, searching for answers. But for now, LQGs remain one of the greatest unsolved mysteries of the universe, a puzzle that challenges everything we thought we knew about the cosmos. Whatever they are, one thing is certain: they are not just ordinary clusters of quasars. They are something far more profound. If large quasar groups are truly real and not just an observational illusion, they force us to rethink one of the most fundamental assumptions in cosmology: that the universe is homogeneous on the largest scales. This principle, known as the cosmological principle, is the foundation of nearly every major theory about how the universe works. It suggests that no matter where you look, things should be distributed in roughly the same way when viewed at a large enough scale. But LQGs don't follow this rule. They are so massive that their very existence suggests something is deeply wrong with our understanding of the cosmos. To put this into perspective, the largest known LQG, the huge LQG, stretches across 4 billion light-years. That's so big that it shouldn't exist under current models. Our theories suggest that structures beyond 1.2 billion light-years should simply not be possible. Yet here we are, observing something that defies that limit by more than 3 times. If LQGs are real, then either we have been fundamentally misunderstanding how cosmic structures form, or there's something influencing the universe on a level we haven't even begun to grasp. One explanation could be that LQGs formed under extreme conditions in the early universe, where the distribution of matter was not as even as we once thought. If some regions had a much higher density of dark matter, it could have led to the gravitational collapse of matter into these enormous structures. This would mean that LQGs are fossils from the universe's chaotic infancy, remnants of a time when gravity was sculpting the cosmic landscape into the patterns we see today. However, this explanation doesn't fully align with our current understanding of structure formation, leaving a major gap in our knowledge. Another possibility is that LQGs are part of a larger cosmic web, an unseen framework that connects galaxies and quasars in ways we don't yet understand. Some researchers believe that these massive structures could be nodes in an interconnected network of matter and energy, stretching across the entire universe. This could imply that the universe itself has an underlying pattern, one that is not random but follows rules we have yet to uncover. If this is true, then LQGs might be the first visible clue that the cosmos is structured in ways beyond our comprehension. But what if LQGs are not just the result of natural cosmic evolution? Some physicists have speculated that these massive structures could be evidence of an unknown force at work, something that actively influences the formation of galaxies on an intergalactic scale. Could there be a hidden force shaping the universe, one that operates beyond the four fundamental forces we currently recognize? If so, this force could be responsible for clustering matter in ways that break our conventional theories. Even more intriguingly, what if LQGs are not natural formations at all, but rather evidence of an advanced civilization capable of manipulating galaxies on an unprecedented scale? If a Type 3 civilization on the Kardashev scale existed, they would have the ability to control entire galaxies for energy, communication, or even travel. Could LQGs be massive cosmic megastructures, arranged intentionally by an advanced intelligence for purposes we can't even imagine? One mind-bending idea is that LQGs could serve as beacons or communication hubs, arranged in specific patterns to signal other intelligent civilizations across vast cosmic distances. If an advanced species wanted to leave behind a message that would be visible for billions of years, what better way than to rearrange entire galaxies into a recognizable structure? This would mean that LQGs are not just random clusters of quasars, but carefully constructed cosmic signals, waiting to be deciphered. But even if we assume that LQGs are purely natural, their existence forces us to ask even bigger questions. What if they are evidence that the universe itself is not what we think it is? Some physicists have suggested that the cosmos could be part of a higher dimensional reality, and LQGs could be the shadows of structures from a higher dimensional space. If true, this would mean that what we see as LQGs are merely the projections of something far larger and more complex, something that exists beyond our current ability to perceive. This theory ties into the idea that our universe might be a simulation, that reality itself is governed by a deeper set of rules we have yet to uncover. If the universe is a simulation, then LQGs could be glitches or intentional design features, hints that we are living inside a constructed reality. If LQGs exist in defiance of the known laws of physics, could they be evidence that our universe was built rather than naturally occurring? As technology advances, we are getting closer to answering these questions. New telescopes, better simulations, and more precise measurements will help us determine whether LQGs are truly real and what they might mean for our understanding of the cosmos. But for now, they remain one of the most perplexing and unsettling mysteries in all of astrophysics. Whether they are relics of the early universe, nodes in a cosmic web, or even signs of intelligence beyond our own, one thing is certain: LQGs should not exist, but they do. And that changes everything. If large quasar groups truly exist as we observe them, then the fundamental principles of cosmology, our very framework for understanding the universe, are on shaky ground. The cosmological principle, which states that the universe is uniform on a large enough scale, is one of the bedrocks of modern astrophysics. It tells us that while galaxies, clusters, and voids may exist, everything should smooth out when we zoom out far enough. But LQGs challenge this assumption by forming structures so large that they defy the expected limits of cosmic expansion and evolution. This leads to a difficult question: are LQGs breaking the laws of physics, or are we simply missing something fundamental about the nature of the universe? If LQGs are real, then it means the universe has much larger structures than our models predicted, which suggests that something beyond what we currently understand is at play. Either the universe has some form of large-scale structure that we haven't accounted for, or our theories about cosmic evolution and the formation of galaxies need a major revision. One of the most fascinating aspects of LQGs is their potential connection to dark matter and dark energy. These mysterious forces make up the vast majority of the universe's mass and energy, yet we barely understand them. Dark matter is thought to provide the gravitational glue holding galaxies and clusters together, while dark energy is responsible for the accelerating expansion of the universe. Could LQGs be evidence of a hidden interaction between these unseen forces? If dark matter is not as smoothly distributed as we assume, it could create massive gravitational wells that pull quasars and galaxies into these enormous structures. This would mean that LQGs are not just clusters of quasars but signs of an underlying cosmic skeleton shaped by dark matter. But there's another possibility, one that is even more unsettling. What if LQGs are not just natural formations, but instead, remnants of a previous state of the universe? Some scientists believe that the universe could be cyclical, going through endless cycles of expansion and contraction. If this is the case, then LQGs could be the last remaining echoes of an older universe, massive structures that survived a previous cosmic reset. This would mean that our universe is not a one-time event but part of an infinite chain of cosmic births and deaths, and LQGs might be some of the oldest remnants still lingering from an earlier cycle. Another idea suggests that LQGs could be cosmic scars left behind by unknown astrophysical events, such as primordial black holes, cosmic strings, or even interactions with parallel universes. If our universe has ever collided or interacted with another, it could have left behind massive gravitational imprints, affecting the distribution of quasars and galaxies. This means LQGs might be clues to the existence of other universes, a visible fingerprint of a much larger multiversal structure. If true, this would be one of the most profound discoveries in all of science, proving that our cosmos is just one of many in a vast, interconnected web of universes. But what if LQGs are not just passive remnants of cosmic history? What if they serve a purpose? Some researchers have speculated that LQGs could be playing a role in the large-scale structure of the universe itself, possibly as anchors for cosmic expansion. If LQGs are real, they might be stabilizing forces, affecting how galaxies form, move, and interact over billions of years. Could they be giant cosmic engines, regulating the balance between structure and void, ensuring that the universe doesn't collapse or tear itself apart? Even more mind-bending is the possibility that LQGs are not natural at all, but artificial. If we assume that an advanced civilization existed billions of years before us, they would have had time to reshape entire galaxies, move quasars, and engineer structures on a cosmic scale. This leads to a radical hypothesis. What if LQGs are intentionally arranged megastructures, designed by an ancient intelligence to serve an unknown function? A Type 3 civilization on the Kardashev scale would have control over entire galaxies, harnessing energy from quasars, stars, and black holes. If such a civilization existed long before us, it's possible they created artificial galactic formations, either as power sources, communication networks, or even massive cosmic messages. If LQGs show patterns or alignments that seem unnatural, it could be evidence of intelligent design on a scale beyond human comprehension. The idea of cosmic engineering is not as far-fetched as it sounds. Theoretical physicists have already considered that a sufficiently advanced civilization could rearrange stars to create a galactic-scale beacon, or use quasars as long-distance power sources. If LQGs were arranged deliberately, they might serve as gravitational hubs, stabilizing regions of space or guiding the flow of matter and energy across the universe. But perhaps the most shocking idea is that LQGs are not just structures, but living entities in some form. Some scientists have proposed that the universe itself could be a kind of intelligence, with galaxies, black holes, and cosmic structures functioning as parts of a greater mind. If this is the case, then LQGs might not be accidental formations but a form of cosmic consciousness, vast structures that play a role in some form of universal awareness. Whether LQGs are evidence of unknown physics, hidden cosmic architecture, remnants of a previous universe, or even signs of intelligence, one thing is certain: they should not exist, but they do. And if we can understand them, we might unlock secrets about the universe that go far beyond what we ever imagined. If large quasar groups are real, they represent an undeniable challenge to our most fundamental understanding of the cosmos. Everything we assume about the large-scale structure of the universe, the way galaxies form and move, and even the nature of space-time itself could be thrown into question. These colossal structures defy our current models, forcing us to consider possibilities that range from new laws of physics to evidence of advanced civilizations or even cosmic-scale intelligence. One of the most perplexing things about LQGs is their sheer size. How can structures this massive exist in a universe where everything is supposed to be evenly distributed at large scales? If the cosmos truly follows the cosmological principle, there should be a limit to how large structures can become before everything smooths out into a homogeneous spread of galaxies and voids. But LQGs break this rule. Some of them stretch over billions of light years, forming patterns and alignments that suggest an underlying order we don't yet understand. Take, for example, the huge LQG, one of the largest known structures in the universe. It spans a mind-boggling 4 billion light-years across, containing 73 quasars arranged in a way that seems almost too structured to be random. According to our current models of cosmic evolution, structures this large shouldn't exist, yet they do. The existence of huge LQG suggests that either we are missing a key ingredient in our understanding of large-scale cosmic structure, or our assumptions about the way the universe organizes itself are flawed. This raises another question: how do LQGs form in the first place? If they are simply natural formations, then something must be guiding their creation. One possibility is that they are shaped by the influence of dark matter, the mysterious substance that makes up most of the universe's mass but doesn't emit light. Dark matter interacts gravitationally, forming web-like structures that act as scaffolding for galaxies and quasars. If LQGs are following hidden dark matter filaments, then their formation might not be as mysterious as it seems. But that still wouldn't explain why they exceed the expected size limits of cosmic structures. Another possibility is that LQGs are a relic of the early universe, formed during a period when cosmic expansion hadn't yet smoothed out the distribution of matter. If this is true, then LQGs could be fossils from a time when the universe was more chaotic and structured differently than it is today. This would mean that instead of forming gradually, LQGs could be remnants of ancient regions where matter was more concentrated before expanding outward. But what if LQGs are something even stranger, something that challenges not just astrophysics, but the very nature of reality itself? One of the more radical theories suggests that LQGs could be evidence of cosmic topology, meaning that space itself is not as simple as we assume. If the universe has a more complex shape, such as being curved or even looping back on itself in ways we don't yet understand, then what we perceive as LQGs might be illusions created by the large-scale geometry of space-time. Some physicists have even proposed that LQGs could be signs of interactions with other universes. If we live in a multiverse, where multiple universes coexist and occasionally interact, then LQGs could be the result of a past collision between our universe and another. When two universes brush against each other, they could leave behind imprints in the form of anomalous cosmic structures, which we now see as LQGs. If this is the case, then LQGs might be the first observable evidence that we are not alone in the multiverse. Even more unsettling is the idea that LQGs might not be passive structures at all. What if they are engineered? If an advanced civilization existed billions of years ago, it might have had the ability to manipulate galaxies, move quasars, and create structures on a cosmic scale. This could mean that LQGs are not random, but intentional formations, created for purposes we can't yet comprehend. Could LQGs be cosmic power stations, harnessing the energy of quasars to fuel unknown megastructures? Could they be intergalactic highways, marking pathways for an ancient civilization that once traveled between galaxies? Or could they be signals, arranged in specific patterns to communicate with other intelligent beings across the vastness of space? If LQGs are artificial, then they could be one of the first signs that we are not the first intelligent life to emerge in the universe. Instead, we might be witnessing the remnants of a civilization so old and so powerful that its structures still persist on a scale so vast, we mistook them for natural formations. But perhaps the most mind-blowing possibility is that LQGs are not just structures within the universe. They might be part of the fundamental structure of the universe itself. If LQGs play a role in the large-scale organization of space, then they might be something akin to cosmic neurons, part of a greater intelligence that spans the entire cosmos. In this view, LQGs could be nodes in a universal consciousness, helping regulate the flow of energy and matter across billions of light years. Whatever the truth may be, one thing is certain: LQGs defy everything we thought we knew about the universe. They challenge the limits of known physics, raise profound questions about the nature of cosmic structure, and hint at possibilities so vast and mysterious that we are only beginning to grasp their significance. Are they merely accidents of nature, or are they signs of something greater, something that could change our understanding of the cosmos forever? The more we investigate large quasar groups, the more it seems like they don't just challenge our understanding of cosmic structure, they outright break it. The entire foundation of modern cosmology rests on the cosmological principle, the idea that when you zoom out far enough, the universe should look uniform in every direction. Matter should be evenly spread, without any structures beyond a certain size. But LQGs are so massive that they shouldn't even exist in a universe that follows this principle. Let's put this into perspective. The current theoretical limit for large-scale structures is known as the homogeneity scale, which is about 1.2 billion light-years. That means beyond this scale, everything should blend into an even distribution of galaxies. But then we discovered structures like the huge LQG, which stretches over 4 billion light-years, breaking this rule completely. And the huge LQG isn't alone. There's also the Claus-Campusano LQG, another massive quasar grouping that spans over 2 billion light-years. Even larger than that is the Sloan Great Wall, a structure so vast that it pushes the limits of what should even be possible. And then, of course, there's the Hercules Corona Borealis Great Wall, the largest known structure in the observable universe, spanning 10 billion light-years. These structures are so large that they make us wonder, is the universe truly random, or is there an unseen order guiding the way things form on a cosmic scale? One way to think about this is by considering the role of dark matter. Dark matter is an invisible form of matter that doesn't emit light but exerts a gravitational pull. Scientists believe it acts as a kind of scaffolding for the universe, forming a vast cosmic web where galaxies, quasars, and clusters take shape. If LQGs are somehow following this hidden dark matter web, then maybe their size isn't as random as it seems. Maybe they are forming along pathways set by dark matter itself, creating superstructures that are larger than we ever imagined possible. But even if dark matter plays a role, it still doesn't explain why these structures break the homogeneity scale. If LQGs are natural, then our understanding of how matter clusters together is incomplete. This has led to radical theories that question the very nature of space itself. Could it be that space-time isn't smooth, but instead shaped in a way that allows these massive structures to form? Some physicists have suggested that if the universe has a more complex topology, meaning it could be curved, looped, or shaped in unexpected ways, then what we perceive as LQGs might actually be distortions caused by the shape of the universe itself. And then there's an even more mind-bending possibility. What if LQGs are evidence of an entirely new force of nature? We already know of 4 fundamental forces: the strong nuclear force, weak nuclear force, electromagnetism, and gravity. But what if, on the scale of billions of light-years, there is an unknown force influencing the way matter clusters? If such a force exists, it would rewrite our understanding of physics, opening the door to entirely new ways of thinking about the universe. Another theory is that LQGs are fossil remnants from the very early universe, dating back to a time before cosmic expansion smoothed everything out. This would mean that they are leftovers from a chaotic, highly structured era, before the universe reached its current large-scale balance. If this is true, then studying LQGs could be like looking back in time to an ancient period when the cosmos was still organizing itself. But perhaps the most controversial theory of all is the idea that LQGs are not naturally occurring at all. What if they were created? If an advanced civilization had the ability to manipulate galaxies on a large scale, it might leave behind structures like LQGs as evidence of its presence. Could it be that LQGs are cosmic-scale engineering projects, left behind by an ancient, hyper-advanced race? The idea of civilizations manipulating galaxies might sound like pure science fiction, but it's actually based on a real concept called the Kardashev scale. This scale measures civilizations based on their energy consumption, ranging from Type 1, planetary control, to Type 2, star system control, to Type 3, galactic control, and beyond. A Type 3 civilization, one capable of harnessing the energy of entire galaxies, would have no trouble rearranging quasars into structured patterns across billions of light years. If this is the case, then LQGs could be the first observable evidence of intelligent life beyond our galaxy. Maybe they are power stations, intergalactic highways, or markers left behind by a civilization so advanced that it reshaped the cosmos itself. Or maybe they are something even stranger, signals. What if LQGs were arranged in a way that encodes information? If they follow mathematical patterns, could they be trying to communicate with other intelligent beings across time and space? If this is true, then we might be staring at the universe's largest message, waiting to be deciphered. Regardless of the answer, one thing is certain: LQGs challenge everything we thought we knew about the universe. They push the boundaries of physics, force us to rethink the structure of space-time, and raise questions so profound that they could redefine our place in the cosmos. And yet, despite all of this, we are only scratching the surface of what LQGs might mean. The more we study them, the more they seem to hint at a deeper reality, one where the universe is not as simple as we once assumed. Could it be that LQGs are the key to unlocking a hidden layer of cosmic order? Are they proof of an undiscovered force, a relic of an ancient era, or a sign that we are not alone? Whatever the truth is, one thing is clear: LQGs are one of the greatest space mysteries of all time. The more we analyze large quasar groups, the clearer it becomes that they don't just challenge our understanding of the universe, they demand a complete rewrite of what we thought was possible. Everything about them contradicts the standard model of cosmology, and their sheer size forces us to confront some of the most unsettling questions in physics. How did they form? Why do they exist at scales that should be impossible? And what do they mean for our understanding of the cosmos? One of the most striking things about LQGs is that they don't follow the expected patterns of galactic formation. In standard cosmology, structures form through a process called hierarchical clustering. Small structures merge over time to create larger and larger formations, with gravity slowly pulling everything together. This model explains why we see galaxies forming in groups, clusters, and superclusters. But LQGs break this pattern completely. They exist at a scale where gravity alone should not be able to bind them together. The sheer distances involved should mean that these quasars are not gravitationally connected, yet they clearly form distinct structures, defying expectations. One possible explanation is that LQGs are not bound by gravity in the traditional sense but instead follow a larger underlying structure in the fabric of the universe. If the large-scale structure of the cosmos is not as random as we think, then perhaps quasars are aligning along invisible pathways, a kind of cosmic scaffolding that determines where massive structures can form. This idea connects to the concept of the cosmic web, the vast network of filaments that make up the universe's large-scale structure. These filaments are mostly made of dark matter, the mysterious invisible substance that makes up the majority of the universe's mass. If LQGs align with the cosmic web in a way that is not yet fully understood, then their existence might not be as unnatural as it seems. However, even if LQGs fit into the cosmic web, there's still the issue of scale. The size of some of these structures, especially the huge LQG and the Hercules Corona Borealis Great Wall, exceeds the theoretical limits of how large a structure in the universe can be. This suggests that our models of cosmic evolution are missing something fundamental. One possibility is that LQGs formed in a much younger universe when the rules of structure formation were different. If the early universe had physical conditions that allowed such massive formations to take shape before the expansion of space diluted them, then LQGs might be fossilized relics of a past cosmic era. This would mean that they are some of the oldest structures in existence, dating back to a time when the laws of physics may have behaved differently. Another possibility is that LQGs are evidence of new physics that we haven't discovered yet. If there is an unknown force or interaction at play, then it could explain why these quasars are clustering together in ways that shouldn't be possible. Some physicists have suggested that LQGs might hint at a fifth fundamental force, something beyond gravity, electromagnetism, and the nuclear forces that govern the universe. If such a force exists, then it could be shaping the large-scale structure of the universe in ways we don't yet understand. There's also a more extreme possibility. LQGs could be evidence that our understanding of space itself is flawed. If the universe has an unconventional topology, meaning that space is curved or connected in unexpected ways, then what we see as a massive, impossibly large structure might actually be an illusion. The quasars in an LQG might not be as far apart as they seem. They could be connected through a warping of spacetime that makes them appear larger than they really are. This would mean that our measurements of cosmic distances need to be reconsidered. Another mystery surrounding LQGs is their distribution. If they were simply random clusters of quasars, we would expect them to appear in a more scattered pattern. But instead, they often form in linear or curved arrangements, almost as if they are following a specific blueprint. This has led some researchers to wonder whether there is a deeper mathematical pattern at play, one that we have yet to recognize. And this leads us to one of the most controversial theories of all. What if LQGs were arranged deliberately? If an advanced civilization had the technology to manipulate galaxies, quasars, or even entire sectors of space, then the structures we see as LQGs could be intentional. This ties into the Kardashev scale, which measures how advanced a civilization is based on its ability to harness energy. A Type 3 civilization, one capable of controlling energy at the scale of an entire galaxy or beyond, might be able to arrange quasars into massive structures for a specific purpose. If this were the case, then LQGs could be signals or markers left behind by an ancient intergalactic civilization. Perhaps they were used as energy stations, acting as beacons across the cosmos. Or maybe they serve as navigational markers for civilizations traveling across intergalactic distances. If quasars were arranged with intention, then they might contain encoded information, a message embedded in the universe itself. But if LQGs were created, then who or what could have built them? Could they be the work of an ancient race so advanced that they have long since vanished, leaving behind only these massive, cryptic structures? Or could they be part of an ongoing project, something still unfolding in the depths of space? And if we ever decipher their purpose, what would it mean for humanity? If LQGs are evidence of intelligence on a cosmic scale, then it could completely redefine our understanding of our place in the universe. We would no longer be isolated observers in a vast and empty cosmos. We would be part of a much larger story, one that has been playing out across billions of years. Whatever the truth is, one thing remains clear: LQGs are one of the greatest cosmic mysteries of all time. They break our understanding of scale, challenge the fundamental principles of cosmology, and open the door to questions that could change everything we know about the universe. Whether they are natural formations, relics of the early universe, evidence of new physics, or the fingerprints of an ancient intelligence, their existence forces us to reconsider the very nature of reality itself. And yet, even as we uncover more about these vast structures, we are left with more questions than answers. Are LQGs the largest structures in the universe, or will we find something even bigger? Do they hint at unknown forces shaping the cosmos, or do they follow patterns we simply haven't deciphered yet? And if they were created, then who or what built them? One day, we may finally unlock the secrets of LQGs. But until then, they remain a reminder that the universe is far more mysterious than we ever imagined. LQGs don't just challenge our understanding of scale, they also raise deep questions about how structure forms in the universe. When we look at how galaxies and quasars are distributed across billions of light years, we expect them to follow certain rules set by gravity, dark matter, and the fundamental nature of space itself. But LQGs seem to break those rules. Their existence suggests that there might be hidden forces, unknown physics, or even something about the nature of reality itself that we haven't yet grasped. One of the biggest puzzles about LQGs is how they could have formed so early in the universe's history. Most models suggest that the cosmic web, the large-scale structure of the universe made up of filaments of galaxies and voids, formed over billions of years as matter clumped together under gravity. But LQGs seem to have assembled far earlier than they should have. This suggests that either the universe was structured differently in its early days, or that LQGs formed through a mechanism that we don't yet understand. One possibility is that the universe had an uneven distribution of matter right from the start, meaning that certain regions were already dense enough to form these massive structures while others remained empty. If this were true, then it would mean that the early universe wasn't as uniform as we thought. The cosmic microwave background radiation, the faint glow left over from the Big Bang, suggests that the early universe was nearly uniform with only tiny fluctuations in density. But LQGs may hint that these fluctuations weren't so small after all. Another possibility is that LQGs formed along filaments of dark matter, which we cannot see but which exerts a gravitational pull on normal matter. If the distribution of dark matter was different in the past, then these structures might have formed in ways that don't match our current models. This would mean that our understanding of dark matter, one of the biggest mysteries in physics, is incomplete, or that there are other forces at play that we haven't discovered yet. But the biggest problem with LQGs is their sheer size. The Hercules Corona Borealis Great Wall, one of the largest known LQGs, stretches 10 billion light-years across. This is so large that it shouldn't even be possible under our current understanding of the universe. The reason is something called the cosmological principle, the idea that, on large enough scales, the universe should look the same in all directions. Structures larger than about 1.2 billion light-years are not supposed to exist, because gravity shouldn't have been able to organize matter on those scales within the age of the universe. And yet LQGs prove that something much bigger is happening. This raises a fundamental question: what if our entire model of cosmic structure is wrong? If LQGs are truly breaking the limits of structure formation, then we may need to rethink everything we know about how the universe evolved. Could it be that the early universe expanded differently than we thought? Could there be a hidden force shaping large-scale structures in ways we don't understand? Or could it be that space itself is connected in unexpected ways, making distant quasars appear to be part of a single structure when in reality, they are much closer together due to the curvature of space-time? One idea is that LQGs might be remnants of an earlier phase of the universe, before the laws of physics settled into their current form. Some theories suggest that in the first few moments after the Big Bang, the fundamental forces of nature were unified as one. If this was the case, then LQGs might be the result of physics that no longer applies, a kind of cosmic fossil from a time when the universe played by different rules. Another radical idea is that LQGs could be evidence of multiple universes interacting with each other. If our universe is part of a larger multiverse, then some regions of space might be influenced by forces from neighboring universes. This could explain why LQGs appear in certain places and not others. If an adjacent universe was close enough to ours in the distant past, it could have left behind imprints in the structure of our cosmos, creating massive formations like LQGs as a result. This would mean that LQGs aren't just mysteries within our universe, but evidence of something even bigger, an entire network of universes shaping each other in ways we can barely comprehend. And then there's the most mind-bending theory of all. What if LQGs aren't just random structures but intentional constructs? If an advanced civilization had access to technology beyond anything we can imagine, they might be capable of moving entire galaxies, or even clusters of quasars, into specific patterns. Some physicists have speculated that highly advanced extraterrestrial civilizations could use quasars as power sources because they are some of the brightest objects in the universe, capable of outshining entire galaxies. If this is true, then LQGs could be evidence of large-scale engineering on a cosmic scale. Imagine a civilization that had the power to arrange quasars into specific formations, either for energy collection, communication, or as markers for intergalactic travel. What if the alignment of quasars and LQGs isn't random, but follows a pattern that we haven't deciphered yet? If such a civilization existed, it would have been active billions of years ago, long before Earth even formed. This means that LQGs could be messages from a long-extinct civilization, encoded in the very structure of the universe itself. If that's the case, then the biggest question isn't just how LQGs formed, but why? What purpose could they serve? Are they beacons? Power stations? Or something even stranger? Perhaps an ancient warning left behind for civilizations like ours to find? As we continue to study LQGs, we are forced to confront the possibility that our universe is far more complex, structured, and perhaps even designed than we ever imagined. Whether they are the result of unknown physics, remnants of a lost era of the cosmos, or the fingerprints of an ancient intelligence, one thing is certain: large quasar groups are one of the most mind-bending mysteries in the universe. And yet, with all the research we've done, we're left with more questions than answers. How many more LQGs are out there waiting to be discovered? Do they fit into a larger cosmic pattern we don't yet understand? And if they were created by some unknown force or intelligence, will we ever decipher their true meaning? One day, we might finally have the answers. But for now, LQGs remain one of the most compelling, thought-provoking, and utterly baffling mysteries of the cosmos. LQGs are more than just a challenge to our understanding of cosmic structure. They might be a clue to something far deeper about the nature of the universe itself. The fact that these structures defy the expected size limits suggests that something fundamental is missing from our theories. Are the laws of gravity different on cosmic scales? Could there be forces we have yet to detect? Or do LQGs suggest that the universe is not as uniform as we once believed? One of the most intriguing aspects of LQGs is how they seem to cluster in specific regions of space while leaving others relatively empty. This pattern suggests that their formation was influenced by some underlying process, one that we don't yet understand. Some scientists believe that these structures could be linked to primordial density fluctuations, variations in the density of matter that existed in the early universe. If these fluctuations were larger or distributed differently than current models suggest, it could explain why LQGs formed in such massive, complex structures. But this would also mean that our understanding of the early universe is flawed. Another possibility is that LQGs are connected through an unseen cosmic web of dark matter and dark energy. While dark matter is known to form a scaffolding for galaxies and galaxy clusters, its role in shaping structures as large as LQGs remains unclear. If dark matter was distributed in an unusual way billions of years ago, it might have created pockets where massive quasar structures could form. Dark energy, which is driving the accelerated expansion of the universe, could also play a role, perhaps influencing the formation of LQGs in ways we have yet to fully grasp. The problem is that we don't have a clear way to test these ideas yet. Our best tools for studying the universe are still limited. The largest telescopes can only observe so much, and simulations of cosmic evolution are only as good as the assumptions we put into them. If LQGs are truly breaking the rules of structure formation, then they may require a new model of cosmology, one that redefines how we think about the growth of the universe. Some researchers have even speculated that LQGs might be evidence of something even more bizarre, a universe that is not three-dimensional, but higher-dimensional. Some theories in physics suggest that our universe might have extra dimensions beyond the familiar three of space and one of time. If this is true, then LQGs might be manifestations of structures that exist in higher dimensions but only appear as large-scale formations in our observable universe. This idea, while highly speculative, would explain why LQGs seem to defy our current models of gravity and structure formation. If these structures are shaped by forces acting in a higher dimensional space, then our existing theories, based on three-dimensional physics, may be incomplete. This could mean that the universe operates on a deeper level than we have ever imagined, with LQGs being just one of many clues pointing toward a hidden reality. Another hypothesis is that LQGs are evidence of cosmic voids on an unimaginable scale. If space is structured in a way that includes massive voids, regions with almost no matter, then the existence of LQGs might be tied to these empty spaces. In other words, rather than being massive formations that break the rules, LQGs might be shaped by the absence of matter elsewhere in the universe. These vast cosmic voids could be influencing the way matter clusters, creating structures that appear far larger than expected. And then there's the question of whether LQGs could be related to cosmic inflation, the rapid expansion of the universe that occurred just after the Big Bang. Some models of inflation suggest that different regions of space expanded at different rates, creating uneven distributions of matter. If this were true, it could explain why LQGs exist in certain parts of the universe but not others. It could also mean that the early universe was more chaotic and irregular than we currently assume. If LQGs are tied to inflation, then they might also be linked to another mind-bending possibility, that our universe is just one of many. Some versions of inflation theory suggest that different regions of space could have expanded into separate universes, each with its own physical laws. If this is the case, then LQGs could be evidence of boundaries between these universes, zones where the physics of one universe interacts with another. This idea might sound like science fiction, but it's being taken seriously by some cosmologists. If LQGs represent regions where different cosmic domains meet, then they could be the first observable proof that we live in a multiverse. If true, this would completely redefine our place in reality. Instead of being just a single universe with definable rules, we could be part of a much larger cosmic landscape, where different universes exist side by side, influencing each other in ways we don't yet understand. Another possibility is that LQGs are not just natural formations but evidence of a cosmic intelligence. If a civilization had technology capable of manipulating galaxies, it might have the ability to organize quasars into massive structures for some unknown purpose. Some have speculated that LQGs could serve as beacons or energy networks for an ancient and possibly extinct intergalactic civilization. Quasars are among the most energetic objects in the universe, producing immense amounts of radiation. If an advanced civilization wanted to harness energy on a cosmic scale, it might find a way to use quasars as power sources, perhaps by aligning them in specific formations that maximize their energy output. If LQGs were artificially arranged, it could mean that someone, or something, was shaping the universe long before humans even existed. Of course, there is no direct evidence for this idea. But given how little we understand about LQGs, it cannot be entirely ruled out. The possibility that these structures were intentionally created raises some profound questions. If an ancient civilization built them, where are they now? What happened to them? And could they have left behind other signs of their existence? As we continue to study LQGs, we may eventually find the answers to these questions. But for now, they remain one of the most fascinating and perplexing cosmic mysteries ever discovered. They challenge everything we thought we knew about the universe, forcing us to consider ideas that range from unknown physics to the possibility of a multiverse, or even the presence of ancient intelligence. One thing is certain: LQGs are not just random collections of quasars. They are something much bigger, much stranger, and possibly far more important than we can currently comprehend. Whether they are natural formations, cosmic fossils from an earlier era, or evidence of something beyond our imagination, they demand our attention. Because if LQGs can break the rules of the universe, then maybe we don't know the universe as well as we think we do. And that realization alone is enough to change everything. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.